you are joining us for the first time, you are very welcome. This is the Apologetics Academy. The website is apologetics-academy.org, and you can click on online apologetics training and you get to sign up for upcoming sessions. Basically, we bring in different scholars, experts, apologists, speakers from across the theological and philosophical spectrum, Muslims, atheists, people with different persuasions and perspectives, to speak on topics of interest to Christians, particularly pertaining to whether Christianity is true. And we also cross-examine and critique other alternative worldviews as well. And then we open up to open floor Q&A, dialogue, discussion, and debate. This week we have Alan Hainline, who's going to be talking to us about the cosmic fine-tuning argument for the existence of God. Then next week, which is October 1st, we have George Yancey, who is a sociologist in Texas, and he is going to be talking to us about Christianophobia. We've all heard of Islamophobia and homophobia, but George Yancey is going to be talking to us about Christianophobia, which will be very interesting discussion. Then the following week, on October 8th, we have atheist Justin Schieber on, who's got a strong philosophical background, and he is going to be talking to us. His title is Disagreement About Religious Disagreement, and he's going to be talking to us about whether religious disagreement can play a part in an argument against theism of some form. So we'll look to see what he has to say there with great interest. And then on October 15th, we have Dr. Andy Bannister on, who was previously working with Robert Zacharias Ministries in Canada, but is now working with Solas in Scotland, in Dundee. And he's going to be talking to us about his book, The Atheists Who Didn't Exist. So that'll be fascinating as well. So as I mentioned, this week we have Alan Hainline. We're going to be having a discussion of the cosmic fine-tuning argument. If you're a viewer this evening or today, wherever you are in the world, there's a number of ways that you can participate. You can simply watch and listen anonymously, or you can participate in the chat window, or you can submit questions anonymously by hitting the Q&A button at the top of your screen, or you can click the raise hand button, and then I will promote you to be a co-panelist with our speaker, and you will have the opportunity to engage the speaker with your webcam and microphone and make your comments, ask questions, express disagreements, ask for points of clarification, just have a one-on-one dialogue before moving on to someone else. But please keep questions on topic, and please be courteous and cordial and respectful, even if you disagree with the content of the presentation. So as I mentioned, we have Alan Hainline this evening. Alan, do you want to maybe just tell us a bit about who you are, just for those that haven't come across you, and then just launch into the topic? That would be awesome.
Sure. So yeah, my name is Alan Hainline, and I live here in the Dallas, Texas area. Married with 4 kids that are now adults in their 20s. And I've always been drawn to this argument, well, for I guess probably since even the late 80s or so. I have a physics degree from UT Austin, and studied some at Biola University in the graduate program there in science and religion. Have a master's equivalent in software and science engineering. Recently taught at the college at Southwestern on some physics and philosophy related issues at the undergrad level, and have taught some for UT continuing engineering studies as well. And yeah, I'm very interested in kind of tracking this argument, and I think it does provide some evidence for God, as I'm going to make a case here. And even if it doesn't, I think it's very interesting. People should really follow what's going on in this realm, because I think there's something significant that will come out of it. I personally am quite confident that it provides at least some evidence for God. But yeah, so should we jump on in then and do some screen sharing? And
sure, go ahead.
Now, is it better if I do a actual slideshow mode?
Yeah, if you go into the presentation mode, that works. Yeah.
Okay. All right. So one interesting quote on the title page here by Paul Davies says, the really amazing thing is not that life on Earth is balanced on a knife edge, but that the entire universe is balanced on a knife edge and would be total chaos if any of the natural constants were off even slightly. Pretty provocative quote, maybe just a tiny bit of exaggeration in saying any of the constants, but beyond that, something worth thinking about. So the plan today then would be to make a case for finely tuned physics. We can discuss that. So kind of at first, just sticking to the physics, like, is the universe fine-tuned for life? That's a claim that's purely a scientific claim. And then we can look at what are candidate explanations. And I'll argue that certain ones that are commonly offered fail, and that the best candidates are either the multiverse or design. And that if it's design, I think there's a pretty good case that the designer would be God at this foundational level of setting up constants and initial conditions. And then we can engage in more extensive Q&A probably then after that full presentation. So one thing I'd like to raise attention to, if you haven't heard, there's a really great book that just came out, at least I got my copy on Kindle this week, and it's by Cambridge University Press by two very prominent physicists. Luke Barnes is younger, so he maybe hasn't established his career for as long, but he's certainly, I think, probably the foremost expert in fine-tuning, having written the most extensive, comprehensive review of the literature on the fine-tuning argument. And he's partnered with a fellow University of Sydney professor there, Geraint Lewis, who also, both of them have PhDs from Cambridge University. And Lewis argues in the book for multiverse as an explanation and Barnes for theism. So it's a really great dialogue. You're getting a lot of great physics. It's geared towards the lay level, but there's a lot of depth there as well. But they do a good job of making it understandable. And I was actually one of the ones that took a look before the book came out and was very impressed then. And the final version, haven't worked my way through all of that, but it looks fantastic. And it's got a great recommendation by Brian Schmidt, who's a Nobel laureate. And so I think this is going to get a lot of attention. Even one like Tim Maudlin, who some of you might remember, he was arguing against fine-tuning at the conference they had in New Orleans as part of the team with Sean Carroll. And he wrote a really nice endorsement of the book as well. So basically, here's the thesis of my presentation. And I'm basing this on something that came out of a debate between atheist Peter Millikan and William Lane Craig a few years back, where Millikan said, I would concede that if there is an inexplicable coincidence in the fundamental constants of nature whose values have to be precisely tuned within a wide range of otherwise available possibilities, that would make a complex universe possible, then this constitutes a phenomenon that very naturally invites explanation in terms of a cosmic scale designer. So I want to basically argue that we have everything that Millikan concedes here, so that we do have an argument essentially for God from this data. So yeah, we'll jump in now to the physics of fine-tuning and just look at what do we learn from physics. Now note that the term fine-tuning is a metaphor, and so some people might mistake it, if you're not familiar with this literature, with equating to design itself, but that's definitely not the case. Within physics, it's more of a technical term that would describe a suspiciously precise assumption. So if you've got a model that requires a very small range for a parameter that's otherwise free, then that would be said to be fine-tuning. And to physicists, the fine-tuning is seen as a clue that there might be some kind of deeper theory, deeper explanation that wouldn't require fine-tuning. So it is, in some sense, it is considered as constituting some reason for doubting a particular theory in favor. If you've got a deeper theory that requires less fine-tuning, then that's something that really needs to be considered. And that's why I think this evidence really does cry out for some kind of deeper explanation. Okay, so now there can be different kinds of fine-tuning, obviously, within physics. Here, we're looking at what is pertaining to life and being life-permitting in the universe. So a bit more background about fine-tuning. We can fly through this pretty quick because I think this is a pretty sophisticated audience. But Some of you might recall the Arizona biosphere set up a number of years ago where they were trying to have self-sustaining life and set up something which, if it worked, they could in principle take it to another planet and have life inside of that. But it was very difficult, they found, to actually construct a self-containing area like that that would be good for life. Okay, so that's really the kind of thing that we can apply to the universe. The whole universe can be seen as a biosphere. Is it something which permits life to exist? And this would be called then the fine-tuning of the cosmos. So I'm going to argue that our universe is finely tuned, and I'm taking this claim straight from Luke Barnes, basically, although I might want to call it intelligent life here, but the claim would be that in the set of possible physical laws, parameters, and initial conditions, the subset that permit life is very small. And I would say that you could almost look at intelligent life in particular, and it might be hard to quantify the difference, but we could certainly think that it'd be easier to get life than to get intelligent life, to get things like bacteria and so forth, versus something akin to humans. You might have additional things that come into play that have to be finely tuned. I think Rare Earth is a good book that kind of makes that case, that they think that bacteria might be quite widespread throughout the universe, but they think that it's quite rare to have an environment where you would have something more permissible for humans. Although I should point out here that I'm not really interested so much in the environmental aspects as the fundamental laws. I'm not going to make a case that our Earth required all these special phenomenon in order to permit life, that it's improbable to have a life-permitting planet among all planets, and more looking at the very fundamental level of laws, the constants governing those laws, and the initial conditions of the universe. Because I think that's a much better argument than the other. I'm not sure the other, I don't really argue that case myself from the environmental. So Barnes, in his review article that I mentioned, he references 200 articles that affirm this claim. And I do want to give credit to Luke Barnes, because I think he is a very careful thinker on this. He's philosophically informed, and he's very knowledgeable. And so I want to credit him. If you see a lot of things in this presentation would be based on his material. So give him credit where credit is due. All right, here's an interesting quote from Stanford physicist Leonard Susskind, where he says, "Science may be undergoing a huge course correction. A titanic controversy has erupted over the pattern of extraordinary unexplained coincidences that are necessary for our own existence." So I did a query. This was a little bit dated now, but it was still, even if the trend didn't hold up, I think rather interesting to look at the number of articles referencing the term anthropic, which anthropic means supporting man, or really mostly what they mean is that supporting observers more generally. But you can see that it is something which is talked about vastly more than it used to be within the peer-reviewed physics literature. So the first question you want to ask, though, if you want to say there's fine-tuning, is, well, is there a wide range of possible physics? And I think here that it's very much in consensus that physicists think the constants could have been different. Nearly all major physics departments are heavily invested in theories that entail constants could have been different, things like string theory especially. And that there seem to be certain parameters, such as spontaneous, the weak angle is thought to have, its value is thought to have been taken on by sort of a random process in the early universe, which is due to spontaneous symmetry breaking. In other words, just like a pencil on its end, would be very unstable and tend to fall in a direction, but it might be very hard to predict which direction. It might be kind of a random thing. Similarly, at least with one or two constants, I think we've already shown that they seem to have an environmental aspect to them. All right, so there does seem to be nothing in our physical theory that dictates initial conditions in particular. So far, the standard model doesn't give you a reason for specifying exactly what the mass of certain particles would be or things like that. There might be a deeper theory that constrains them somewhat, but deeper theories like string theory open up, I think, a wide variety of possibilities. And certainly with respect to initial conditions, there doesn't seem to be anything that would dictate how those would be set. The other question that is very important to consider and has had some discussion from the likes of Sean Carroll lately, but is the question of how do you even determine what physics is life permitting? And here I would want to point to the work of John von Neumann, where he showed mathematically essentially what's required for any self-replicator. And he did a lot of good work in the cellular automaton area. And he really was interested, though, in the question of what can you build that would be a self-replicator and evolve, which I think is what we would need to reach any kind of intelligent life. And so he really showed in a very rigorous way, I think, that you need some kind of information storage system. You need stable structures, therefore, that could store information. If it's rapidly changing, for example, it's very difficult to store information on the surface of the sun because it's such a chaotic environment. It's hard to have stable structures there. They're constantly changing. So it seems you need something like chemistry. It doesn't have to be chemistry, but something like that to have information-bearing systems. So you also need information processing systems to be able to carry out the replication. You have to be able to harness energy from the environment for the work of replication. Otherwise, you would run into second law problems. So you do need something like stars for long-lived stable energy source. It wouldn't have to be stars, but it would have to be something that would give you a long-lived stable energy source. So we'll kind of fly through some examples of fine-tuning here. There are 4 fundamental forces of nature, and you do have to get them in the right balance to have life. There are a number of fundamental particles that also turn out to require fine-tuning in terms of their masses. Now, I list protons and neutrons on here. Those are not fundamental, but they turn out, I think it is worthwhile to also consider fine-tuning as it pertains to things which aren't necessarily fundamental, but especially if you can quantify the effect as you work it back into the fundamental parameters. So I think all of those are worth considering in terms of the particle masses having to be fine-tuned. There's a number of cosmological parameters as well. Matter density, energy density, number of dimensions of space even. It turns out life is only possible in 3-dimensional space, according to many physicists. And things like dark energy and dark matter also have some aspects of fine-tuning as we're learning. The surprising thing about dark energy is that, not that it exists, but that it's not more powerful than is predicted by quantum field theory. So many of these, it turns out, are finely tuned to something like 1 in 10 to the 36, sometimes more, sometimes less. The particle masses, it's harder to quantify what scale there, but if it could vary up to the Planck mass scale, then there would be an incredible degree of fine-tuning. Maybe there's something fundamental that would keep it from being that large, though. But nevertheless, we have many cases which are sort of a mind-boggling level of precision. So let's unpack this a little bit more. There does seem to be some fine-tuning required for long-lived stars. The relative strengths of 3 different forces have to be finely tuned to slow the rate of nuclear reaction. If you think about what a star is, it's basically a controlled nuclear explosion held together by gravity. And so it is a little surprising that you can have stars that live in a stable form for, say, 10 billion years, sometimes much more than that if they're smaller stars. It also turns out if we start playing with the masses of different particles, that will also mess up the rate of nuclear fusion or whether it goes at all. If gravity can vary up to the strong nuclear force, which seems like a reasonable assumption to many physicists, then you would end up with fine-tuning to 1 part in 10 to the 34th. I think Barnes, even on his blog, he quoted something a little bit more improbable than that. But in general, I try to use the most conservative figures I can find in these different areas. And so there do seem to be a number of fine-tunings that could give a stable energy source. If the neutron mass was even just 1 part in 1,000 heavier, then stellar fusion would fail. And as Fred Hoyle pointed out many years ago, there seem to be several coincidences involved in making both carbon and oxygen in stars. Each seems to impose a fine-tuning of about 1 part in 200 or so on the strong force or the electromagnetic force. There's been some good work recently done on supercomputers that seem to confirm these older predictions. But these were what led Hoyle to say that there were no blind forces we're speaking about in nature. And what's interesting, I think, is when you start looking at these fine-tuning constraints, you end up seeing that you end up with a lot of the same constraints for both stars and something like chemistry, which, you know, why would they necessarily overlap at all? It's rather interesting that you have an overlap that just works out for different life-bringing criteria in different realms, and it happens, the same value happens to satisfy all the constraints. All right, let's look at gravity in a little more detail in the context of star formation. So, yeah, again, if it can vary up to the strong nuclear force, you've got various constraints to keep stars from burning out too fast or being overcome by degeneracy pressure. Stars could easily lose their mass to radiative pressure if you don't have things in the right balance. All right, as Susskind hints at here, you know, a lot of physicists think that gravity could have easily been much stronger than it is. It's an unexplained miracle. He says that gravity is as weak as it is. He doesn't mean a literal miracle there, by the way, as he's more of an atheist in his background. But yeah, I think it's some compelling evidence here. And let's look then at quark masses. And I included a quote here just to kind of remind folks that sometimes the response, and when people first hear the fine-tuning, is to say, well, hey, the universe is just adapting to laws of physics, you know, through evolution and so forth. But I think, you know, the physicists studying this, they do have they have assumptions that the Darwinian evolution could accomplish quite a bit, but they're looking at things that would prohibit life from ever getting off the ground. If you can't get evolution started, then it doesn't matter how powerful the process is. So Craig Hogan here says that, yeah, changing the quark masses even a small amount has drastic consequences for which no amount of Darwinian selection can compensate. There's 8 different articles or more on the quark masses. Recent ones seem to be affirming it. Some of the kinds of disasters you have would be that there's no protons or neutrons in the universe, or no carbon or oxygen. They seem to be pretty major problems for life of any form. And the fine-tuning is roughly to about 1 part in 10 to the 36 if you combine all of these. There's an article here that Barnes highlights in his peer-reviewed article and in his presentations at the Philosophy of Cosmology by Stephen Barr and Almas Khan. They have an interesting plot here that has the ratio of the down quark to the Planck mass and the up quark to the Planck mass plotted in this 2-dimensional plot in log form. And they zoom in on that one square and show all these different constraints that would seem to be life prohibiting. I think at least 8 out of the 9 are pretty clear cut. There's one of them that I think Luke Barnes has done some more work, and he's saying, well, maybe that one is not a clear cut case. We might want to pull that one off. But even if you do, you're left with this tiny, potentially viable area. And as Susskind again says, you know, these up and down quarks are absurdly light. They're 20,000 times lighter than particles like the Z boson. We need an explanation for that, and the Standard Model has not provided one. And when you do the analysis, he also agrees if they were much heavier, it's a total disaster. Now, these are big numbers. Most of you maybe have a science background, I don't know, but this is something I use in popular presentations that I think is a powerful illustration of how improbable 1 chance in 10 to the 36 would be. Consider that you take 1 grain of sand, color it red, mix it in a sand pile of normal sand that you haven't colored, that would cover all of Eurasia and up to the height of the moon. Okay. Now, actually, of course, you couldn't build a sand pile that high, but this is just a thought experiment, just picturing the rough idea of how many grains of sand 10 to the 36 would be. So if you randomly select the 1 red grain of sand, that's about 1 in 10 to the 36 probability-wise. All right, another commonly cited example of fine-tuning, which has led to a lot of discussion, is the cosmological constant. It affects the expansion rate of the universe. If it was larger, if it was anywhere even close to its natural value, the universe would have expanded so fast to be a thin hydrogen soup with no chance of life. Barnes points out that the density would soon become about 1 hydrogen atom per size of our current universe in density if this was a few orders of magnitude bigger than what it is in our universe. If too small, the universe would rapidly recollapse before life can form. So many people quote that this is fine-tuned to 1 part in 10 to the 120th power. I'll go with the lowest figure I've seen anywhere in the literature, that it would be 1 in 10 to the 53rd power. And again, I've come up with an analogy. If you think of a bullseye the size of 450 million light years in diameter, and hitting the bullseye being just the size of a bullseye on a normal dartboard, the odds of hitting that through a randomly thrown dart is about 1 in 10 to the 53rd power. So that's a really big dartboard, because light can travel 33 round trips per second between New York and Los Angeles. So think of how far it could travel in 450 million light years. And if those kind of numbers aren't enough, you should consider the initial conditions and the level of fine-tuning there. So it turns out that nearly all initial conditions of the Big Bang would have resulted in a lifeless black hole universe. Roger Penrose is, I think, the first one that computed these odds, but many other people have confirmed them. But he puts the odds against life at about 1 in 10 to the power of 10 to the 123rd. So not just 1 in 10 to the 123rd, but 1 in 10 to the power of 10 to the 123rd. So writing out that number in normal form, like if you just included all the zeros, you wouldn't have enough particles in the universe for every zero in that number. And he considers whether the multiverse might help with this, but he says that it's actually worse than useless in explaining the anthropic fine-tuning for this parameter anyway, because it predicts exponentially more, exponentially smaller universes. So multiverse predictions are so vastly different than what we find in our universe that he views that as reason to consider multiverse proposals and explaining this worse than useless. I'd also like to argue that it's not as though our fine-tuning claims are going away over time. I think it's held up quite well to a lot of scrutiny since it was first discovered in about the late 70s or so. And we are, I think, discovering some new fine-tuning over time. There was an article recently, it was not too long ago anyway, 5 years or so ago, they did some analysis for, it's been known for a long time that water has exceptional life-giving properties that are very kind of unusual. That's vastly different than other liquids. And the fact that ice floats, that evaporative cooling works so well for organisms to cool themselves, that capillary action works as well as it does because of the viscosity of water. All these different features we've known about for a long time, but it's now understood that if the way that quantum effects had not canceled nearly exactly, we would have ended up not having those life-giving properties. There's this incredible delicate balance. And so, yeah, it's another example of fine-tuning as to why it produces those effects. All right, so yeah, there's a lot more that could be said about water that we don't have time for, but it actually does come into play even in the hydrogen bonding and DNA, different things as well. It turns out that we're discovering that the ratio of dark matter to normal or baryonic matter turns out to also require some level of fine-tuning. It may not be as fine-tuned, but the galaxies only form at high peaks of the dark matter density. Back in 2012, this Ohio State astronomer found some new fine-tuning related to the relative masses of neutrons and protons that was necessary for planetary formation. I'll be the first to admit that some of these newer claims are not as well established as the older claims, where people have been writing papers about them for many years now and scrutinizing them. But I think the overall point is that the number of claims is growing, not shrinking over time. And this was a slide that Luke Barnes presented at the Philosophy of Cosmology, just showing all the connections between the fundamental parameters at the bottom and some of the different things that seem to be necessary for life. And as you can see, there's many lines here. If you change the weak force, you might mess up supernova and how they expel their elements to make them available in planets for life down the road. You might also mess up other things, as you can see from this hodgepodge diagram. So in summary, many cases of fine-tuning are to a mind-boggling precision, and it's in terms of the initial conditions, the constants, and it's definitely seems to be the case in my research, the very few physicists who have really studied it. I've met some who haven't studied it, who doubt it, but of the ones that are really have studied, read many of the peer-reviewed articles, et cetera, they seem to be quite in agreement with the data itself. Now, that obviously the interpretation, people are going to come down on different sides on that. Now, there was, of course, the well-known skeptic Vic Stinger, who he wrote the book, which I bought, called The Fallacy of Fine-Tuning. But I really do think that Luke Barnes' peer-reviewed article was an excellent refutation of that, and that if you look at the interaction that Stinger and Barnes had online, it's accessible. You don't see Stinger really responding when Barnes says, for example, that 6 out of 8 equations in his monkey guide program were simply incorrect. You don't see Stinger trying to argue against the fundamental claims that Barnes was making. And so I think even if you don't know that much physics, someone could easily see that it seems like Barnes really won that argument. But I encourage you to look at it yourself. If you think Stinger had some strong arguments, look at Barnes' peer-reviewed article, look at some of their interchange online, and make your own decision. So often the other thing that I find striking is that there are multiple life-permitting constraints that have to be satisfied for a given finely tuned parameter. So if these life-permitting ranges were sort of chosen at random as to where they would even lie, what are the odds that they would overlap at all? I think that's a challenge to the multiverse, as we can discuss later. So I think my thesis that I put up at the beginning, we haven't fully reached there, but I think I've established some parts of this, or at least argued for them, that there is here again was Millikan's challenge to Craig. He said that he would admit that there's a good argument for God if there's an inexplicable coincidence in the fundamental constants of nature whose values have to be precisely tuned within a wide range of otherwise available possibilities that would make a complex universe possible. Now, I would admit at this point, we haven't done anything towards showing that it's an inexplicable coincidence, and that's the focus of the next part of the presentation. But at this point, I would like to open it up to a bit of interaction on whether or not people think that the physics itself, a case for fine-tuning in physics, does this argument succeed? Are there some problems people might want to discuss, or anything that anybody would want to add to the discussion?
All right. Well, if anyone wants to raise a question or make a point or interact with Alan, then just raise your hand and I will ensure that you have opportunity to talk to Alan and make your questions known. We have a hand already from our good friend Stephen Tilley. Go ahead, Stephen.
Hello. Hey, what's up, man?
All right, good. Go ahead.
Just a little question that came to my mind because, as I pointed out in the chat, William Lane Craig and Lawrence Krauss had a few debates, and I watched both of them. What really caught my attention was when Krauss was asked. Krauss basically stated that he's glad he doesn't know how the universe came to be. And I just wanted to touch, there was something I wanted to touch about that. Also that, which is his name, Michiko, I can't remember his name. He said that though with physics, it doesn't leave out the possibility that God could have created all this, that had his divine origin. But also the other side is that it doesn't necessarily point. Basically, it could go either way. I was just wondering, where is physics in regards to pointing towards a creator? And also, do you have any good material for, say, a layman to study physics with?
Okay, I would really highly recommend this book by Barnes and Lewis that's just come out, because it is written for a lay audience. And it lays out a lot of interesting physics, and it is specifically dealing with this fine-tuning issue and looking at different possible explanations. Both authors argue strongly against anything other than the God or multiverse, and then they're kind of arguing with each other. You can see how they make their case and with regard to those. So I think that's a good book. There's a number of other good books on fine-tuning for lay people. Martin Rees has a book called Just Six Numbers, which is a nice intro. And I would recommend, Paul Davies has written some good works on those. Those are a little bit older, but they're still relevant. As far as, general physics books for lay people, I mean, Brian Greene is a popular author. He tends to talk a lot about string theory and so forth in his books. But if you can get past that in terms of, well, nothing against string theory, but just that I think there's a little bit too much focus. It would have been great if he's pretty good at writing and explaining physics concepts. And in some ways, I wish he would focus a little bit more on that than the string theory, speculative aspects. Yeah. But I hope that helps. But yeah, I want to not necessarily get into my own case for why this would point to God, because that's my presentation coming up. But wanted to open it up for interaction on the physics aspects. Like if people think that, well, I'm not sure that physics really is fine-tuned, if they want to discuss that or interact with any of the points that I've made so far. What were your thoughts, Stephen? Is there anything that do you agree that it seems that small change, like if you randomly chose the constants of nature, do you agree that it does seem pretty unlikely that you would end up with a life-permitting universe?
Yeah, I'm pretty much familiar with the argument that if just the smallest iota, forgive me because my knowledge of physics is very dismal, but yeah, I'm familiar with the argument that basically just the slightest move would endanger our existence on this planet. So yeah, the Earth is fine-tuned in a very specific setting where intelligent life can exist. So, okay. And also, like I said, regarding string theory, that itself, I'm familiar with that one too. Basically, that argument runs into problems because then you have to push the question further, and then that's where it runs into a brick wall. At least that's what I'm familiar with.
Yeah, the presentation I'm focusing on today would deal with, well, the physics we do understand that's well established, and if string theory turned out to be true or not, that's a whole separate question. I think we can make a case. The case I'm trying to make is based on known physics. We can consider how, if string theory was true, it might interact with this. It would help the multiverse in terms of giving you a greater landscape for the possibilities for the constant. So it might help some in that sense, but you would still need to also show that you do have a multiverse, and then you could look at its predictions and evaluate them. So we'll get into that later. Mm-hmm. That aspect.
All right. I just wanted to ask all that because, again, my knowledge of physics is almost non-existent. But yeah, just want to throw that out. Ask about all that.
Yeah, well, I applaud your efforts to want to learn more physics. I think everyone should. It's it's the fundamental level of science, really. So it's important.
Mm-hmm. All right.
Okay.
Sure. Thanks for the interaction. Hey, Jonathan, kick me, dude.
All right. Next up is Seth. Seth, you are live. Go ahead. Hello, Seth.
We lost Seth.
Hi.
Hello, Seth. Are you there? Okay. I can't hear Seth. Okay, I'm gonna bring up someone else. Seth, there's something wrong with your microphone. I can't really hear you very well. I'll bring up someone else, and then we'll come back to Seth to see if he's got his problem sorted. Just bring up John.
Jesus. All right. I was kind of curious about this discussion of the probability of life, because it seems to be quite pertinent, but I don't see how we would come up with the probability of life to be possible.
I would agree that it's very difficult to, for example, put an overall number on the improbability of life as you vary these different parameters. But if you look at the physicists writing the articles, they tend to make pretty conservative assumptions, and they look at issues where the universe could go very wrong, for example, in just the level of complexity. So for example, if there are no elements other than hydrogen or none other than hydrogen or helium, in its final form, not just its initial form of the universe, then we know that there would essentially be no chemistry, and it would be very difficult then to satisfy von Neumann's criteria for life, needing an information storage and processing system, etc. So I think, yeah, a lot of these things, yeah, it's hard to put an exact probability number on it, but you can look at very conservative assumptions. You still end up with something that seems to be highly improbable across a large number of lines of evidence. And so when you make a cumulative case, even if you can't put an exact number to it, it sure is attention grabbing when you're dealing with these kind of numbers with a cosmological constant and so forth.
Yeah, no, honestly, fine-tuning, I mean, I, of course, accept the fine-tuning argument, but it always seems to me kind of like it can never make it concrete. It's when I mean, I kind of almost sound like Victor Stenger on this. It's all these initial assumptions. Oh, I'm trying to make this formal, trying to make sense out of this. I wonder how we get these initial assumptions. Yeah.
Yeah. Well, some of them come out of the standard model, or the way that it's viewed commonly with respect to particle masses is that we don't really it doesn't seem to make sense that a particle could have a mass up to the Planck mass, because then it would be a black hole, and that doesn't seem possible. Or even if it was possible, it would certainly be beyond what we could evaluate. And so from an epistemic standpoint, we have a limit there of what we can evaluate. And yeah, if they really could vary up to that limit, then there's just this incredible improbability to the life permitting range. And even if you make more conservative assumptions, just that, say, any particle could weigh as much or have its mass as high as the most massive particle, then that also turns out to require an incredible amount of fine-tuning. Maybe it might be helpful to look at one example with respect to cosmological constant. So there we know from quantum field theory that contributions to that constant, that there would be a number of them based on the different fields, and the magnitude of the contributions is about 120 orders of magnitude greater than the net overall value that would be life permitting. And so you have this near perfect cancellation. And so historically the thought was, well, there's probably some symmetry that just forces them to cancel. We'll find out that the constant is zero, nothing to explain. But in the late 90s, studying supernova, we discovered that the universe is accelerating in its expansion, and that therefore there seemed to be this small positive value for the cosmological constant, and it removed seemingly any natural way to explain how it could have taken on that value, where you have this near perfect cancellation. There's also a contribution from Einstein's general relativity, the field equations, that's unknown. But the important thing there is that the cumulative combined effect has to be incredibly small for life. But what are the odds? If you and I and everybody on this, you know, say you had 5 people choose numbers between 1 and 10 to the 120th power, it could be positive or negative. What are the odds we'd end up summing those together and getting the value of 1? So that it gets people's attention.
Yeah. Well, thank you for answering my questions.
Sure. Thanks a lot, John.
All right. We have other questions as well, and we have one hand raised and we have 3 submitted questions. So let me just do a couple of submitted questions and then we'll get to our hand. Seth submitted a question. Obviously his internet connection wasn't the best. He says, my question is, you mentioned that Penrose's analysis considered the multiverse hypothesis, but which model of multiverse does he consider? Could you elaborate more on this?
That's a great question, actually. Yeah, because there are so many theories out there that one could ask, well, how does he know? Well, which multiverse theory are we even talking about? So there is a little bit of a weakness in that argument, but I would say that the leading theories, certainly like eternal inflation and so forth, do make predictions of larger, or they make predictions doing these kind of fluctuation models that it would be more probable to have smaller universes. But even if you had multiverse theory that didn't favor necessarily smaller or larger versions, you still have the other aspect of Penrose's argument, which would be namely that it's exponentially easier to fine-tune universes that are smaller. So he finds it very surprising on multiverse theory on general grounds that you would have a life-permitting universe that would be of this large size. One way to think of it, and by the way, Sean Carroll's written on this too, and he also agrees that the multiverse and an anthropic multiverse explanation fails for the low entropy condition of the universe. And you can think of it by thinking in terms of what do we need for life? We certainly don't need anything more than our solar system. We could survive quite well with just the sun and the planets. Maybe you don't even need all the planets. It's a little bit debatable how much they might help or hurt on asteroids. But maybe if you had nothing else, maybe you don't even have to worry about incoming asteroids from other solar systems, etc. So yeah, I think that there are some general grounds. They might be a little bit weaker on some multiverse theories than others. But given that the eternal inflation model seems to be the most popular, I think his critique is especially important. But because of the difficulty of fine-tuning large universes, I think it does apply on general grounds, unless you had a multiverse theory that exponentially favored ones of this huge size.
Jason McCool asks, hey Alan, have you looked at the effect of tectonic activity on life? I've been hearing more cases of astrobiologists concluding that an extrasolar planet could not support life unless it also had seismic activity. So it seems like this adds yet another constraint on life in the universe. Yeah,
that's something that you do find a number of people talking about, the tectonic activity enabling recycling of nutrients kinds of things. And planets which allow for tectonic activity would seem to be more likely to be able to support a long-lived magnetic field. So yeah, it's difficult, I think, to apply that necessarily to the kind of fine-tuning I'm making in this argument, though, but it may well impose some additional constraints, but I don't know how you would really work that back to the fundamental constants. So here I am taking a fairly narrow view of fine-tuning and just arguing in terms of at the very most foundational level of physics that you could evaluate in terms of the fundamental parameters and the initial conditions. How sensitive are those to permitting life?
Okay, let's go to our hand and then take the other questions that are submitted.
Yeah, hopefully we can get to the rest of the presentation fairly soon here.
Yeah, sure.
Because that'll probably generate even more questions and interesting interactions when we actually try to explain this.
Sure. Robert, you're live. Go ahead.
Can you hear me?
Yes, we can.
Great. Okay, great. So I just was wondering some clarification. You said in one of your slides, nearly all initial conditions of the Big Bang would have resulted in a lifeless black hole universe. I'm wondering, I interpret that, meaning that the laws that were the mathematics that we have today to explain the Big Bang actually does not explain a expanding universe. It would explain the black hole universe, as you said. Is that what you were sort of implying there?
Well, the argument by Penrose and others goes something like this. It's recognizing the early universe had to have this incredibly low entropy. And when you account for gravity, the entropy is going to obviously has to increase over time. The amount of usable energy goes down due to the second law. And so he actually was able to do some computations, and the way he did them, it related to using the equation for the entropy of a black hole, which then allowed him to draw some conclusions about how special that would have to be in terms of those initial conditions. So it's not necessarily to really understand how the Big Bang came about or what was the physics before Planck time. We don't really need to answer those questions as long as there's this understanding that the second law seems to apply, that you're going from lower entropy to higher entropy. And it looks very surprising that our universe would have such low entropy that allows for things like stars, these long-lived energy sources, that you would have this much usable energy this late in the development of the universe. If you start looking at all possible ways of arranging particles, it becomes very surprising. One thing he did was he said, picture as you go towards a black hole, gravity collapsing, the entropy is getting bigger. That's the more probable thing. If you have a lot of matter at some point, if you have enough of it, a black hole becomes inevitable, and that's higher entropy state, and it keeps eating away at things and so forth. And so the argument is that, well, this really would be the more probable state. It's very surprising that the particles would be spaced out just right to minimize black holes. You might think, well, yeah, there's a lot of black holes, but according to these calculations, which seem to be widely accepted by other physicists, it is very surprising that we didn't have maybe either one big black hole or at least a universe so dominated by black holes that one would see it as being impossible for life. For example, we know that if you get near the galactic core where there are black holes residing, the amount of radiation coming off of those would just rip apart stable structures that would be information bearing of the type needed for evolution and life.
All right, let's go to we've got just a couple of submitted questions, and then we'll go back to Alan's presentation. Raj asked 2 questions. He says, Kevin Sharp, who has recently debated with William Lane Craig, gave an argument against the fine-tuning argument in a Facebook discussion. He says, here are 3 thoughts on fine-tuning. First, fine-tuning is based on the contrast between physical constants, initial conditions, and the natural laws. However, we have no basis on which to draw this distinction with any confidence because our 2 best theories of the physically relevant natural laws, quantum field theory, which is the basis for the standard model of particle physics, and general relativity, which together with the basis for the standard model of cosmology are incompatible. We already know they can't both be true, so we have no basis for even being confident about what the physical constants and initial conditions are, much less how they might depend on more basic features of the universe. He says, second, the fine-tuning argument appeals to divine psychology, that a god would create...
Would it be better, perhaps, I suggest we deal with these one at a time, maybe?
Yeah, go ahead.
All right, so the first one, I would, and again, maybe some of these are getting more into the part of the presentation that would come later. Yeah. But I think at least we could point out, I don't see that he's right in saying that we have any basis for being confident about what the physical constants are. We certainly know many of the constants of nature to, some decent level of precision. It is true that there's a fundamental, we know that we need a quantum theory of gravity. We know that general relativity and quantum physics, even though they're incredibly well established and seem to be accurate to 10 decimal places or more in many of their predictions, when you go down to the scale where they both have something to say, we don't really know how to answer those questions. But the thing I think to think about is that these fine-tuning arguments, many of them are based on knowledge that has to be the case at low energy physics. Like, we know what the force strengths are in the low energy case. There is actually, we speak about the coupling constants that relate to the strength of the electromagnetic force, for example, sometimes called the fine structure constant. And that does vary a bit with the energy in the universe, but very quickly after the early universe, it got locked into its current value. And we have a very good confidence of what that value is. We make these astronomical measurements. If the fine structure constant changed, it would affect the way the hydrogen spectra looked, et cetera. So, I think we certainly know the constants, and I think, although obviously physics is not done, I don't think we should just throw our hands up and say we don't know anything here, because we certainly, we have good reasons for thinking that we're not going to overturn low energy physics with new discoveries. Okay, yeah, we don't know, as you probe higher energy physics that go beyond what the LHC can determine, then sure, we don't have a good handle on that, obviously, but to think that low energy physics, that the value of these particle masses and constants is somehow wrong, I think is ill-founded.
Right, the other question is more pertinent to the second half of the presentation. Do you want to maybe save this one for later?
Yeah, let's save that, but you can maybe make a note to make sure that we cover it.
Yeah. All right. Do you want to continue?
Okay, sounds good.
We do have one other hand that's just gone up. Should we take this, or should we just move on?
I think at this point we should move on for sake of time, if that's okay.
Sure. Go ahead.
But let's make sure and give that person a chance later to interact in the next round.
Yeah.
All right, let's see. Okay, so now we'll look at the fine-tuning. So this was taken, now Luke Barnes has given many presentations on this, and he's noted the common responses over time. And this came right out of the philosophy of cosmology presentation he gave. And I think he even roughly tried to order these from the explanations that fail pretty miserably to the ones that are like, well, yeah, maybe we need to consider that, to the better ones being at the end, basically. And so this is just the overview slide of what we'll be talking about, but you might glance at that and see if, see which ones you think are really important. We could spend more time on those. In many cases, I have 3 or 4 slides about some of these, but I'm planning to just kind of fly through them pretty quickly here. All right, so there's some additional ones. These are ones that they're very important for the argument to succeed. And we need to really think through these. But I am going to make the case that many physicists make that really there's really pretty good reasons for rejecting most of these 1 through 14 or other ones. We can talk about other ones if they're not on this list as well. But I think it does boil down to, as Bernard Carr said, if you don't want God, you better have a multiverse. And in this book, it seems that both the atheist author Lewis and Barnes seems to be a theist, because he's arguing for theism here, but they both seem to strongly agree that these other explanations are inadequate to explain the fine-tuning. And so they would want to opt for multiverse or God. And I think both of them see a little bit of force on each side, but they do seem to pretty strongly favor their particular interpretation, which makes it a great book, I think. All right, so let's fly through some of these. I kind of even skipped the first one, that it's just a coincidence, because when there's this many coincidences, it's generally not a good thing to just totally ignore them. You need to look for some kind of explanation. Some people would say that, well, wait a minute, we've only seen one universe, so the probability of a life-permitting universe is 1 out of 1. Sounds a bit like frequentism, I guess you would say, which is very much out of favor among physicists for a probability theory that's practical in the work that's done. So I think it's important to think about what we're really doing here. We're evaluating theories based on how well they explain the data. So I think a really good example that might shed some light on what the case we're really making from fine-tuning is to consider the theory of continental drift. Okay, so these continents do match up pretty well, but more importantly, there's mineral patterns that span them right at the boundaries. If you were to try to piece them together, you end up with this kind of interesting fit. And that applies as well to fossil evidence. So someone could say, well, the probability the fossils would be there is just 1 out of 1. We can't really draw any conclusions here. No one would say that. What you're looking at, you're comparing the theory that these just happened by chance to coincide versus the theory that, no, these were at one time together. They got separated, drifted apart over long periods of time. And so that theory would clearly be more supported by this data. So the theory of continental drift was confirmed because the data was deemed too improbable on the static continents hypothesis. Basically, because we can do theoretical physics, we can predict what happens in other possible universes or other possible scenarios. Or you could consider the example if you made a 20-sided die, even if no one had ever done that, you've never done any experiments with one, if you had good reasons for measuring it, for thinking that it was really symmetrically constructed with equal densities, you would have a pretty good idea to expect 1 out of 20 chance of rolling a 1. And fine-tuning then is really dealing with what we call epistemic probabilities. People might also say, well, okay, improbable events happen all the time. Why is this something that's crying out for an explanation? And they would say that someone has to win the lottery, which really, depending on the lottery, is often not the case. But for fine-tuning, it's more akin to the comparison of the same person winning many, many lotteries in a row by buying one ticket each time. At some point, you might suspect cheating in that scenario. All right. Now, we're going to talk later about the multiverse. Sure, if you have enough tickets, somebody's going to win in all probability. And that's where the multiverse comes into play as a possible solution. But there you're multiplying your probabilistic universe, your resources. I think it can be helpful to consider the fine-tuning first from the standpoint of, let's assume there's just one universe. And I think there you do clearly end up with significant problems for these explanations. And then you can ask, well, what happens if we think there are multiple universes, and how do we weigh the pros and cons in that realm? And it is true that we only know of one universe at this point in terms of empirical evidence anyway. And so as far as we know, there's just been one ticket bought to this cosmic lottery, which is far more improbable. It's about 1 in 10 to the 7th or something of that nature, 10 to the 8th chance of winning a lottery by buying one ticket for most of the lotteries out there. Depends on the lottery, obviously. So you can see that's much less than the kinds of improbabilities we've been dealing with in the fine-tuning. And the other thing, when people say this, they seem to forget that, well, many times scientists do draw conclusions from improbable events. You can see this even, for example, in inferences towards common ancestry. The thought is the same mutations occurring independently would be too improbable, so they would argue that it supports the hypothesis of common ancestry. There's many, many examples like that. Basically, we have a good framework, a methodology for assessing improbable events relative to different hypotheses, namely Bayes' theorem or Bayes' probability. And it can tell us whether certain data support a hypothesis or not. You can make relative comparisons. And so what I'm trying to argue in this is that naturalism is extremely unlikely to have produced life-permitting universes. I think the physics bears that out, with the possible exception of the multiverse, which we can discuss later. But I think certainly if there's no multiverse, that statement seems fairly non-controversial. All right, I've already talked about Stinger, but yeah, he was one of the few physicists to question fine-tuning itself. Really, Barnes in his peer-reviewed article, he's basically dissing Stinger's book. And I think he makes some very powerful cases that much of the physics was wrong, some of the philosophy, even challenges that Stinger really understood fine-tuning and what it meant in terms of the kind of argument that Barnes has anyway. And he drew a lot of conclusions from his Monkey God program where 6 of the 8 equations were wrong. He left out this epsilon fine-tuning factor, one of Martin Rees's 6 numbers. And he only considered one life-permitting criteria, whereas really you need to consider multiple life-permitting criteria. So I think that fails. There's really no silver bullet physicists out there that has shown that the physics itself is wrong. Most people that study it seem to agree that yeah, there's something significant going on here. But you know, at the lay level, sometimes people will say, well, you know, evolution will find a way, or they'll say, well, you're just being too narrow-minded about life forms. There could be other life forms where it's far easier to be life-supporting. But here's Lightman of MIT saying that if these fundamental parameters were much different from what they are, it's not only human beings that would not exist, but no life of any kind. It is true that some of the finely tuned parameters, it's a little bit debatable. Is it a strict limit against any kind of life? And that's where maybe adding the adjective intelligent life pushes it more in the direction of, well, it'd be really hard to get intelligent life in such a universe. But there's enough of these very clear-cut cases, like the cosmological constant. If that was very much bigger, the universe would have just been blown apart, such that there would be a very low density and it wouldn't have had time to fuse together hydrogen into helium, etc. And thus you wouldn't have chemistry, you wouldn't have information storage. How can you do information replication if particles only bounce into each other every trillion years or so? So there's some catastrophes out there. I already mentioned this quote by Hogan. I mean, these physicists writing the articles, they seem to be, I think, pointing out some very severe issues that would prohibit life. They're assuming evolution can do quite a bit. The question is not what can evolution do once life starts, but can you get life to begin with at all? Barnes has done some good discussion of consideration of the best alternative candidate to carbon, namely silicon. But as most chemists will point out, silicon seems to be in every way less helpful than carbon for the kinds of things that life needs. Long chain molecules are less stable. If you oxidize silicon, you get something, silica, which is a solid, not a gas, which organisms could easily exhale, basically. And the more important thing to consider is that because silicon, it's a higher, basically the way you make these elements, and only a few came out of the Big Bang, the real low numbers, most of them are made in stars, but you're just slamming together these atoms and forming, you're fusing them together. Well, you have to make carbon on the way to making silicon. And so universes where silicon is abundant would also have carbon. So it really is not adding much in the way of giving you additional ways in which you could support life, just by saying, okay, yeah, life could have been silicon-based. And the other thing to note is that most of these life-permitting things that we've been discussing don't say anything about the form of life. It's only the Hoyle formation of carbon and oxygen in stars that really relates to that. But it could have been the case without certain nuclear resonance levels that you would have had a bottleneck that prevented anything above carbon from forming. So that would have also prevented silicon. So this is just showing how many more compounds you can make with carbon and hydrogen than the other low-ordered elements. This was one when I was debating a head of a science department at a high school one time, and he was saying, well, this universe is just as likely as any other. The universe had to have some set of constants, so who are you to say that that these are any more likely than any other? And here's where Barnes had a really great response to this objection. I think he said, well, suppose we're playing poker, and every time that I deal myself 10 royal flush, I deal myself a royal flush. This happens like 10 times in a row. At some point, probably well before it reaches 10, you're going to become very suspicious that I'm cheating. And if I were to say, well, hey, this set of 10 hands is no less improbable than any other, so you can't say I'm cheating, we all recognize that that wouldn't really fly in that scenario. You might struggle to put your finger on, well, what really did go wrong? But if you think about the assumption inherent in this claim, the poker hand being just as unlikely as any other, well, that's something that would not be the case, for example, if the constants of the universe were intentionally selected. Then it would not be the case that any set is just as likely as any other. So on naturalism, I would agree that any set of constants is just as likely as any other, but the right question would be, if the dealer dealt 10 straight royal flushes in a row, what's the probability she's dealing fairly? What's the probability that these were set at random, that the cards were really shuffled and dealt at random? I think we would recognize that the probability is pretty low that they were dealt at random if you got that many in a row. Some would say, well, do go to the experiment. I can't draw any conclusions about how improbable life would be. We can only observe our universe. Well, experimental physics is what led to our understanding of the constants, of the initial conditions, of the laws. So we've done a lot of experiments, and they've told us that there's some significant problems. There's also a branch of physics that's not just experimental, but theoretical. And the kind of theoretical physics being done in fine-tuning is exactly the same as done with, it's not just like fine-tuning, it is fine-tuning, as Luke Barnes would say. And we know that theoretical physics has a long history of working well. Obviously, people can have wrong ideas about it, but the powerful thing about the fine-tuning evidence is that you have so many examples, so many lines of evidence, it seems very unlikely to think that people are wrong about all of them. This is a very common objection that should be discussed. People will say, well, the universe doesn't look like it's fine-tuned for life. It's mostly inhospitable to life. I can't go visit the vacuum of space or these faraway places. It doesn't look like it was designed for life at all. But notice that this fine-tuning claim is not claiming that life could live in every square centimeter of space. I think what they're really getting into here sometimes are theological presuppositions. If they're arguing against design by saying the universe is inhospitable. I think the thinking is that this is not how God would have done it. But theists have pointed out there are some logical reasons why he might have. Now, I would agree that it's hard to play the mind of God here, but note it's the skeptic that has the burden of proof, I think, in showing that God couldn't have a reason for making it this way. And we can at least brainstorm and see some reasons why he might have. God might have wanted a huge universe to humble us or show his glory. It's actually the large size and the old age of the universe that can be seen as evidence against most multiverse theories, actually. All right. And then if you think about, well, what would you do about it? If you start adding matter to fill in these voids, you end up with a density that would cause a rapid recollapse in the universe. And if you want these stars to be closer to you and things like that, well, you've got problems with the radiation. It's better to keep these very powerful things distant. So I think this argument is sort of a tangent that doesn't really deal with the core fine-tuning claim, and that it really would be hard for you to show that this is how God would have had to have done things on a design inference. All right, other people would say, well, there's kind of life chauvinism involved in the fine-tuning. Why focus on life? The universe could be said to be finely tuned for black holes or rocks. Here's one skeptic's way of putting it. But one interesting thing about this claim is recall that the Penrose fine-tuning data shows that actually there was a great deal of fine-tuning that seemed to be necessary to prevent, or to minimize rather, the number of black holes in the universe. So it's actually seems to be optimized at minimization of black holes, and that does seem to be a natural consequence from most initial conditions would have been more black holes. All right, so I don't think people, the physicists writing these 200 peer-reviewed articles, they're not necessarily assuming that life would have to be carbon-based or human-like. I don't think there's necessarily this strong bias towards what life would have to be like. And one thing I might point out here too is that on theism, it doesn't seem very surprising that God would want at least some intelligent life that could know about him, that could interact with him. But on atheism, there's nothing that would there's no mechanism for setting fundamental constants that would somehow bias them towards their future effect on producing life or sustaining life. And when you look at how skeptics argue against God, they frequently will raise the problem of evil, which is a very significant challenge, I'll admit. Although I think there's good responses, but yeah, if you raise the problem of evil, you're presupposing though that God would favor life, I think. So I think you can see from the way skeptics argue against God that the inference that God would want life somewhere in the universe seems to be fit quite well with that. This is more than I think I'm just going to fly through here. A little bit overlapping with the last slide. For sake of time, I want to make sure we have a lot of time to discuss these things. These objections are getting, I think, better as we move along here, but Sean Carroll raised this at the Philosophy of Cosmology. We don't even have a good definition of life, so how can you say things are fine-tuned? But I think if you're careful and you really look at things like the von Neumann criteria for life of any kind that could evolve, you end up with some things that are very hard to see how they would even be possible if you had, again, going back to the example of the cosmological constant, if it was much bigger, then you would have, no ability to store information or replicate it in the universe. That seems very clear-cut. So even though we don't have an agreed upon definition of life, we know that there would be nothing worthy of the name life in such a universe. And then most fine-tuning is actually constrained by multiple life-permitting criteria. So even if we were wrong on one or two of them, we end up being right overall. You just need one of them to go through. All right. Another important consideration is the effect of what I would call the anthropic principle. Okay, so many would say, which is right, and it's something that needs to be accounted for. We can only observe that we're in a life-permitting universe. Elliot Sober put this quite well in an objection. You know, what would you think the person that walked around saying there are no square circles, that it's impossible? And so why are we surprised about fine-tuning when it's impossible to observe a universe which is not life-permitting? But I think that is mistaken. In the case of the square circle, that deals with what's logically possible. But here it's logically possible that there wouldn't have been a life-permitting universe, even though in that universe there would have been no one there to observe it. I think if you consider the example also, John Leslie came up with this example of the firing squad. Consider that you were put before a firing squad of highly trained marksmen at point-blank range, ready, aim, fire, boom, but they all miss. Would you infer there might be some deeper explanation, or would you say, well, if I wasn't alive, I wouldn't be here to observe it, so there's nothing to be surprised about? No, I think that would be surprising in that scenario. You're not surprised that you do not observe your dead, but you're rightly surprised that everyone missed. The unlikelihood of the situation demands an explanation. Philosopher John Hawthorne, he was a philosopher, the lead philosopher of metaphysics at Oxford University for about 10 years. And he used to be one that was not seeing the force of the fine-tuning argument, but has recently changed his view on that. He sees something pretty significant in fine-tuning now. He has some good observations where he talks about, he says that there are some things we can learn where we couldn't have learned the opposite. I couldn't have learned that I don't exist, okay? But he says it's awesome evidence that there is something rather than nothing, just from the fact that I exist. So you can have evidence for something, even if it was impossible to observe it otherwise. So I think that's a kind of a good, simple example that people can wrap their heads around. The fact that I couldn't have learned I didn't exist doesn't stop the fact that I exist being awesome evidence. Okay, he also talks about a firing squad, a little different context, saying, what if there's two boxes of guns, one faulty and one not? You survive the firing squad. Wouldn't you take that as awesome evidence that they used the faulty guns? Even though it's true that if you hadn't survived the firing squad, you would not have been there to learn that you survived it, because you wouldn't have survived it. So you can still have evidence for something, even if there is sort of an anthropic selection effect. And that's what it's best to think of this as, is a selection effect. You're not getting a random sample of data. It's biased by certain things. And that's something that physicists are pretty used to dealing with, and I think they're accounting for it well in these arguments. I mean, in order for there to be this kind of selection effect, though, you need a population. And so you need something like the multiverse to give you these other chances at life. And I like the way Hawthorne summarizes this. He says the other thing about this objection is its irrelevance. We're not talking about the relevance that the universe is life-permitting, but the evidential relevance that life-permitting physics is rare. We could have learned this to be false. That's what's gotten everybody's attention. No one thought there was a fine-tuning argument until they realized how narrowly fine-tuned these different parameters are for life. All right, some question, well, how well can we assess an exact probability? We talked about that a little bit a while ago, but some more thoughts. Consider the question of what, if I played LeBron James in basketball, what are the odds that I would win? It would be incredibly low. Maybe if he randomly died at that particular time, I would win, or got a really bad injury. He'd have to have a bad injury to even win in that scenario. But even though I couldn't quantify that, I could still reasonably conclude that it's unlikely. And we've got all these different parameters that seem to, on fairly conservative assumptions, seem to give us these incredible levels of improbability. We may not know the exact distribution function, and I think there's some pretty good arguments for just using the principle of indifference. If you don't have any particular reason to think otherwise, then just assume the different possible values are equally likely. And that's really where you get these kind of quoted probabilities. Aguirre and Barnes have argued that we can generally approximate probability by assuming a linear or power law distribution, and that there's some interesting quotes by Aguirre that Barnes quotes, and that they even interacted with live together at the Philosophy of Cosmology, where they argue that if there was something to explain this fine-tuning, it would require it being peaked in this very narrow range. And so you would still end up needing some finely tuned parameters to make it peak in that narrow range. And so I think it's really hard to explain away this data, given that there is a wide range of possibilities. All right. An important consideration too would be, is there an underlying law that explains fine-tuning? So if all the constants and the initial conditions were driven to the values they have by a law, then out of necessity, they would have those values, and there's no sense in which you could say that they're finely tuned, that it's improbable. Okay, but I think there are some interesting considerations here that, let's say that was the case, you would still have an issue with the initial conditions because, as John Wheeler said, never has physics come up with a way to tell with what initial conditions the universe was started off. And nothing is physics clearer than what is not physics. I was able to have a class with Wheeler when I was at UT Austin, and he was a great guy to lecture. And he was the one that coined the term black hole and some other contributions that were pretty significant. But anyway, so would a theory of everything, you hear that thrown out a lot, would that result in one possible set of laws? Well, in the past, there was some optimism towards that through string theory, but now it's viewed more as, instead of a theory of everything, more like a theory of anything. So string theory seems to increase the number of possible values for constants. It seems to transfer them from, there might just be like maybe one string coupling constant or something like that, but the parameters do become environmental on string theory. Depending on how you compactify the 11 dimensions that you need for string theory, ends up resulting in different constants of physics. And so these things become more environmental parameters. And so it might help you in a multiverse scenario to give you an explanation of the fine-tuning, but it certainly doesn't drive them to one possible set of laws. Paul Davies has a strong quote on this. He says he thinks it's demonstrably wrong. There's not a shred of evidence the universe is logically necessary. Indeed, as a theoretical physicist, I find it rather easy to imagine alternative universes that are logically consistent and therefore equal contenders for reality. If you go back to the time of Aristotle, that's when they thought that, oh, you can just sit in your room and think about how the universe should have been and figure it out. But the long history of science has shown that that's not the case. You have to go do experiments. There's no underlying law or principle that's driving everything to be a certain way within the universe. Really, most physicists would say no to this question of a theory of everything, making the constants take on certain values. Frank Wilczek, Nobel Prize winner, says it's possible, but I think it really strains credulity. Carr and Rees point out more generally that even if all these anthropic coincidences could be explained, it would still be remarkable that the relationships dictated by physical theory happened also to be those propitious for life. You would still have these remarkable coincidences that would seem to need an explanation because there's no logical necessity in the values taking on these certain values that they do, the constants taking on the certain values. Just a couple of weeks ago, they had this large conference in Poland talking about varying constants and fundamental cosmology. The whole conference was devoted to people considering the fact that the constants could have been different. And so I hear this at the lay level a lot, but I think among physicists, people there's so many ways to vary the constants if there are additional dimensions, if something even remotely close to string theory is true. There's many different ways that we could have variable constant. John Barrow has a good article on this that I could point people to if they're interested, where he gives like 5 reasons to think the constants could have been different. And I just realized I haven't been plugged in on my laptop. I need to do that real quick here. So the next part of the presentation, we're going to consider I think the most plausible explanations of the fine-tuning, namely either God or the universe. Yeah, not all physicists would say it comes down to those two, but it seems to be a growing trend toward that, and many of the ones that seem to have studied it a lot and thought about it, even if they're skeptics like Lewis and Susskind, would say, yeah, there seems to be a need for a multiverse to explain this, if you're not going to have God as the explanation. Susskind says, in fact, that the stakes are to accept the string landscape, and he admits that it results in this kind of dilution of the scientific method because of the inherent difficulty of validating something like string theory or other universes But he says to do otherwise would be to give up science altogether and accept intelligent design as the explanation for the choices of parameters of the standard model. So seems to have a strong bias against even considering intelligent design, but yeah, he seems to think that these other explanations fail significantly other than one of those two, and he obviously seems to reject the intelligent design option. Yeah, I'm getting too distracted here. Let me grab the power cable. So I think most of you probably know what a multiverse is, but it's simply this theory that there are vast numbers of other universes. And when people apply the multiverse to the fine-tuning, usually they're then saying that, well, hey, if we have all these universes, that could give us the probabilistic resources to adequately explain fine-tuning. Okay, and what I want to do then is just say that there's some challenges to that. Let me plug this in. All right. So the first challenge would be, do you get enough universes from a multiverse theory? So in many of these, I think it passes this test. Certainly internal inflation does. The most popular theory gives you just an incredible number of universes. But you know, there might be other multiverse theories that don't pass this test. I think at minimum, based on the evidence we've seen, you would need more universes than we have subatomic particles in our known universe. So that's kind of interesting. And I think you can reach that even if you just take a subset of the clear fine-tuning levels that we talked about. But think about this. What if I bought, say, 10 to the 100th lottery tickets? That's about the number of particles in the known universe at the subatomic level. But if I chose my favorite numbers in every ticket, it would help zero, right? Because I have the same chance of winning if I bought one. I'm just splitting up the prize with myself a large number of times. It's really dumb. So obviously there's something else that you need from a multiverse explanation as well in order for it to be adequate in explaining the fine-tuning. Namely, you need a way of changing the constants. You need different initial conditions in the different universes. And they need to vary widely, not just a little bit. There are different, depending on the theory for how the constants change, there's different understandings considering how much the variability might be. But it seems that you might well need something like string theory. There's a lot of different proposed theories that would allow the constants to change, which wouldn't result in a sufficiently wide variance. Now, it is true that it's oft quoted that, hey, there's probably 10 to the 500th different possibilities for constants on string theory, but there are other theorists that don't necessarily go there. People might think it's more like 10 to the 10th, which I don't think would be enough. But I think that the bigger challenge for string theorists is, well, how confident can you be in that number given that we can't really write down the equations for string theory yet even. So it's very difficult to know for sure what the right level of variability is. But I think it's not unreasonable to think that it could vary widely enough on string theory. That seems pretty reasonable. So we'll assume that it passes that test as well. Now, it is also the case, though, that over time, string theory was very highly acclaimed in the past, and it's not quite as widely accepted these days, but there's still a significant number of people that are optimistic about it, even though there seem to have been a number of predictions that just haven't really been borne out. Most recently, I think just a few weeks ago, there were some bets that had to be paid up where people had been betting that they would have already found evidence for supersymmetry at the LHC, Large Hadron Collider. But now that we've explored some higher energy levels, we still haven't seen any evidence for supersymmetry, which still may well be there, but at least counts as some. Well, string theory, most people would acknowledge that if string theory is true, that supersymmetry has to be true, this feature of the universe that relates to a new kind of symmetry that's never yet been proven, and which had to have been broken at our energy levels to support life, by the way, as well. But all right.
The first thing I want to emphasize is, we do have to be careful about the provisionality of this.
Showing
I mean, in some of the
skepticism
debates, for example, about Hawking's book, you almost get the impression that some people, not Hawking himself, but some people are saying, well, of course, science now knows the answer to this question. It's called M theory. Actually, it's not really. It's just a staging post along the long road of science. We try to make sense of things. At the moment, this looks quite hopeful, but it's clear that further work needs to be done. And the question is, well, will that take us in future? So,
well, I'm going to say I think it's actually stronger than that.
Okay.
That what is referred to as M theory isn't even a theory.
Yes.
It's a collection of ideas, hopes, aspirations.
Exactly.
It's not even a theory. And I think the book is a bit misleading in that respect. It gives you the impression that here is this new theory which is going to explain everything. It's nothing of the sort. It's not even a theory, and it certainly has no observational. Partly it's this 10 to the.
All right, so we see there that there are at least some significant scientists, such as Penrose, that seem to be rather skeptical about the ability of skeptical about string theory in general. And that's probably the best hope for giving you enough variability for the constants to explain away the fine-tuning. But yeah, there's others that are more optimistic. There's nothing conclusive from that, but I think it's worth noting there's a little bit of bias. If you're just out there reading journal articles in the popular level press, there's a lot more hype about string theory or the multiverse than you necessarily see, I think, in the peer-reviewed physics literature. So another challenge to the multiverse as an explanation of fine-tuning would be that the theory should predict life-permitting universes which would not be too dissimilar from our universe. And so that's where Penrose's critique that we've discussed already comes into play. But there are other things as well. One way to think about this, to see why this is important, would be to consider, again, the firing squad example. On the hypothesis that the firing squad was aiming at you, but they all missed, you would expect the pattern of bullets to maybe be pretty close to you, maybe right above your head or to your side. If you had enough firing squad members shooting at you, you might have a really nice outline of your body up there, because they probably, if they're true marksmen, they probably have a relatively small average aiming error, and therefore they're more likely to barely miss than to miss by a lot, and you can draw some conclusions from that. And this is the same kind of reasoning that's being attempted to be applied to the multiverse, as we're considering whether it's a good explanation for fine-tuning. And yeah, the jury's out on that, but there are a number of problems where it just doesn't even seem helpful at this point. There seem to be some parameters that are overly fine-tuned. And by that, you could say, well, it's not strictly necessary for life, but it's helpful, or it's helpful for certain aspects of life. Hawking points out the quark masses seem to be roughly optimized for the existence of the largest number of stable nuclei. We don't need all of those heavier elements for life to exist at all, but they certainly enrich our lives on Earth by all the different things that we can do using those available elements, and it probably helps life some as well, some of the heavier ones. Frank Wilczek has pointed out that proton lifetime is at least 10 orders of magnitude greater than is necessary for life. And so it's surprising, if there was a multiverse even, that we would end up having so few proton decays that we haven't yet detected one. Water, a lot more could be said about water, but that was one that was kind of recently we discovered how finely tuned that had to be for life. But all these special properties, they're probably not strictly necessary for life, but they sure help it a lot. We can keep lakes from freezing over with this ice forming at the top and then acting as an insulator. Moderation of temperature, both at the level of Earth and within an organism, are greatly helped by the high heat capacity of water. There's a maximal ability for water to cool organisms because of the latent heat of evaporation. Many more that could be said that are surprising, unusual properties of water that make it incredibly well suited for life. In terms of transport within cells and within the Earth, both. It's got some great properties for dissolving things, etc. Weathering, the way that ice freezes, since it expands, it breaks up rocks, it helps recycle nutrients. Water plays a very active role in protein folding. The water molecule gets involved in helping to establish the 3D shape. Morowitz, a biologist, says the proton conductance is almost unique to water. It's a key element in the biological energy transfer. So this most biofriendly compound just also happens to be very abundant. We would expect evolution to choose the most biofriendly compounds, but there's no way in which biological evolution could make water so biofriendly. And so it seems to be supportive of fine-tuning beyond what's strictly necessary, and therefore beyond what could be explained just by a brute force, throw a lot of universes out there, and eventually you're going to get one life permitting. Well, yeah, you'll eventually get one life permitting, but if it has other special features, I think Luke Barnes used the analogy that suppose a transportation device is what's being selected for or something. Yeah, you might have random ways of putting things together to form a car, and you might have a selection effect if you can only live if you drive in a car, say, or something. But I think I'm getting this a little bit wrong, but I think you'll see the main point will stand. But it would be very surprising, though, if that car had a built-in GPS capability, because that had nothing to do with its ability to transport you around. And in the same way, we seem to have some things that go beyond what's strictly necessary that seem to show a special biofriendliness to various fundamental aspects of physics and chemistry. All right, a fourth challenge for the multiverse is that if a theory leads to absurdities, it gives us good reason for rejecting the theory. According to Vilenkin, eternal inflation requires the Everett many-worlds interpretation of quantum mechanics. Now, that may or may not be true, but many physicists strongly reject this notion that every quantum event could lead to a parallel, or maybe a better term would be a perpendicular universe. And Vilenkin points out that the ramifications of his multiverse theory actually result in there being regions in the multiverse where Al Gore is president, and yes, Elvis is still alive. So it's really funny seeing these kind of things in a peer-reviewed article. So the question you want to ask is, to put it more precisely, I think, is that, okay, you got a multiverse theory you propose. Let's look at what would be typical of the observers it produces in your multiverse theory. And if they have properties that are so different than what we see in our universe, it might give us reasons to be skeptical of that multiverse theory. So namely, one thing that comes into play is this so-called Boltzmann brains problem. The Boltzmann brain paradox is this, that it's more likely that a brain randomly forms out of the quantum vacuum with false memories than that we have this huge improbable universe in which life came about billions of years later, and eventually we have this intelligent life. Okay, so consider that John Page has written, for example, that if any vacuum which is capable of supporting observers eternally inflates, again, that's the most popular multiverse theory, such a vacuum produces an infinite number of Boltzmann brains. And a couple of other authors say that to exhibit a paradox in the global description of multiverse, the overwhelming majority of observers arise from quantum fluctuations and not by conventional evolution. So recall that I said this anthropic principle is a selection effect. You're selecting for observers. But if the observers are predicted to be different than what we find in our universe, not just a little different, but vastly different, then I don't think that would make that multiverse proposal not a good explanation for the fine-tuning of our universe. And I'll admit, there are ways around this. Sean Carroll's written some ways around this, but the thing seems to be the case that you had this initial round of articles where people were on very general analysis saying that this is a natural byproduct of the theory of eternal inflation. But I think if you can tweak some parameters, if you can do some fine-tuning, basically, you can get around the Boltzmann brain problem. But again, the problem is if you have to do fine-tuning to avoid this problem, then have you really removed fine-tuning? I would argue not. Now there are some recent data that we're getting that we need to analyze. The Planck satellite measures the cosmic microwave background radiation, and a few years ago there was a significant amount of new data that came out that allowed us to evaluate certain multiverse theories, etc. And this guy, the gentleman seen at the top right there, Paul Steinhardt, he makes some pretty good arguments that we have some reason from this data that would mitigate against the multiverse, and in particular, the leading multiverse theory of eternal inflation. And he's got much more to say about this. So this is one provocative statement. Just so you know, Steinhardt is not some lightweight. He's the director of the Princeton Center for Theoretical Physics. He's the Einstein Professor in Science. So he's kind of in that chair now. It's got one of the cooler titles around there. But he says in a multiverse, each measured cosmological parameter represents an independent test of the multiverse. In the sense, one could expect large deviations from any one of the naive predictions. The more observables one tests, the greater the chance of many deviations from the naive predictions. Hence, it is surprising that the Planck 2013 data, that's the data 3 years ago from this Planck satellite, that it agrees so precisely with the naive predictions derived by totally ignoring the multiverse and assuming purely uniform slow roll down the potential. In other words, he's looking at a version of inflation that wouldn't necessarily entail the multiverse and saying, well, this explains the data. We don't need to, and in fact, he says it's surprising if there was a multiverse version of this that you would have the measurements that we actually had. Because these kind of multiverse scenarios, this chaotic inflation ends up producing wildly varying things. And so why do we get this simple version of things that is exactly what you would predict with a much simpler non-multiverse model? And then finally, one more thing that a multiverse must overcome if it's going to be an adequate explanation of fine-tuning is that it should not itself require fine-tuning, or that would just shift the problem up a level. I've already given an example of this in the previous discussion, but consider that even Sean Carroll says that the probability of inflation occurring in a universe where you have the initial conditions chosen at random is about 1 chance in 10 to the 66 millionth power. So that looks like a lot of fine-tuning to me. Now, there might be ways around this, but certainly if you just look at the history of inflation, there was a lot of ways in which the theory was originally described in ways that wouldn't work. So you can see that it requires fine-tuning just by looking at the history of inflation proposals. There was a graceful exit problem. It turns out it was hard to get inflation to stop. And if it never stopped, you certainly would never have life because you just have this runaway expansion. So in summary then, we've seen these 6 challenges, and I spend the most time on the multiverse because I think it is the best alternative to theism for the fine-tuning. But as you can see, at least I think, and I think there's a number of other physicists or many philosophers think the multiverse is not a good explanation of the fine-tuning. But often they're underestimating some of the physics that drives you to either God or multiverse kind of options, I think. But the questions, yeah, does a multiverse produce vast numbers of other universes? Some of them do, some of them don't. The most popular theory, eternal inflation, certainly passes that test. And if string theory or something similar as that is true, you could probably pass number 2. Although there was some debate, I pointed out some versions of string theory wouldn't necessarily give you a wide enough variability. The theory should predict life-permitting universes, which would not be too dissimilar from our universe. Many multiverse theories fail on that, in particular eternal inflation. And I don't see that they've solved the Boltzmann brain problem in an adequate way without introducing some fine-tuning. And the simple fact is we have no empirical evidence for any universe other than our own. And if anything, I mean, we have some very prominent scientists seeming to argue that we might have evidence against this leading theory. And whatever the case, we need to look at the theories being proposed with respect to whether they require fine-tuning. I think if you stop and think about it, some kind of generation machine that can just, put out huge numbers of universes, it's probably a well-oiled machine, not one that you could just be expected to derive at random naturally. I mean, that's a pretty phenomenal thing. And certainly the leading universe, the best multiverse theories they've come up with so far do seem to require fine-tuning in my understanding. All right, this is basically, I meant that to be a background slide. Okay, is this evidence for God? So I think there was a good quote from Sherlock Holmes that I'll probably butcher, but it's something to the effect of when you've eliminated all other possibilities, then the other possibility left, even if you think it's improbable, is your best explanation. And so I would challenge people, if you don't believe in God, at least consider this as evidence for God that would make it more likely that God exists, given this evidence. And then that's basically an argument from Bayesian probability theory, the likelihood principle. Fine-tuning is predicted on theism, but surprising on atheism. There was no reason to think that it would have required this kind of fine-tuning for life. There was no, once you learn that life is highly improbable on randomly selected constants, that doesn't sit real well with atheism, where the notion is that there would be no, in principle, way of explaining this most fundamental level of physics other than, well, they must have just been set at chance, or certainly not by any process which had in mind the development of future intelligent beings. And so I think it does favor God over, this evidence favors God over the theory of naturalism, that there's not something beyond nature. Okay, and some might say, well, how do you know that God would even want life? I think it is plausible that, even if you put a low probability here, by the Bayesian argument, you still end up with a good argument for God's existence, because unless you get something that's so, unless you want to say it's improbable that God would want life to the level of the fine-tuning, it's not going to be a defeater for that. You're still going to end up with some evidence from this for God. Okay, and if you say otherwise, that God wouldn't want intelligent life or wouldn't want to leave evidence, that's inconsistent with two very common objections to God: the hiddenness of God, that God should have left more evidence. Here seems to be a case that he did. So how can you say that it's improbable that God would want fine-tuning in the universe? And the problem of evil, which presupposes that God would care about life. So I think you've got some good reasons for thinking that on theism, God would favor life, would favor fine-tuning. And so I think I've argued fairly well that for this concession that Millikan made, where he conceded that if there's an inexplicable coincidence in the fundamental constants of nature whose values have to be precisely tuned within a wide range of otherwise available possibilities, that would make a complex universe possible, then this constitutes a phenomenon that very naturally invites explanation in terms of a cosmic scale designer. So I think the evidence from the fine-tuning does naturally invite explanation in terms of a cosmic scale designer. We could, there might be some debate about exactly how strong that is, but I think it's fairly strong because of these incredible levels of improbability. And you could point to other skeptics that would also seem to admit that fine-tuning is possible evidence of design purpose in creation and the choice of the laws. There's other things that could be brought in play to distinguish between a multiverse and God. You could argue that a designer would be more expected to favor intelligence. The ability of humans to discover scientific truths would seem to be rare among evolutionary possibilities. It's surprising that we can understand quantum mechanics and general relativity given enough study. Thomas Nagel makes some of these points. Consciousness, you could have evolution and natural selection work quite well without ever having conscious beings. Even if you assume that eventually we'll discover a physical mechanism for consciousness, which I think is what atheism is committed to, or at least naturalism would be anyway, the illusory nature of these emergent properties would point to their being very rare. In other words, it's really hard to know how do you mix together chemicals and make them self-aware. It's got to be a very rare phenomenon. And so that in itself could point to an additional kind of fine-tuning that you would expect on theism, but would be surprising on atheism. Things like the perception of free will, objective morality might also contribute to that. All right, but what about some other common objections? This is giving up on science. And here I think Barnes has a good way of saying this, that positing God as a cosmic designer is not replacing a scientific explanation, but adding a personal explanation. And then I added this other part here saying, if you think about Aristotle's different way, there's different kinds of explanations that can be offered for things. And really the proposal that God set up the laws of physics, it's not competing with science. You're still, let science go, finish, do its work. There's good reasons for thinking even when science is done, you end up with these fundamental parameters that would be finely tuned. And therefore it still could support the argument for God. It could be evidence for God. And it would be no more giving up on science than adding a personal explanation to why the water is boiling. You could describe the chemistry of water boiling or just the physical aspects of phase changes, but it might not be the full explanation. That's the question. Is there an additional explanation? Science in principle wouldn't have an explanation for the most fundamental laws, constants, and initial conditions. There's nothing that would drive them to a particular value once you get to that most fundamental level. All right, it's also sometimes said that, well, this is just another God of the gaps argument. But I would argue that there's really no gap here. This is based on knowledge, not ignorance. It's certainly true that science will always progress, we'll learn new things, but all we can do is evaluate based on what we know now. And everything we know now about the foundations of science leaves us with a series of startling coincidences. A fundamental constant is defined as not being derived from a theory. What we're dealing with here is at the most fundamental level. If it is truly fundamental, then science is done. Now, sure, there might be some theories out there that make these not fundamental, but it seems very implausible to think that, and this is where some of those quotes by Wilczek and others, Rees, come into play, to think that there would be no coincidences once you have a final theory of everything. And really the thing to think about too is this uncertainty relates to high energy physics. That's where we don't really understand things very well, admittedly, but fine tuning is very dependent on low energy physics. There's simply too many cases of fine tuning to think this evidence will go away. And just to give you one example of someone that was impacted by this data, Frank Tipler. He was one of the original authors of this very important book that came out in the 80s by Baron Tipler, Anthropic Cosmological Principle. And he says this provocative quote: "When I began my career as a cosmologist some 20 years ago, I was a convinced atheist. I never in my wildest dreams imagined that one day I would be writing a book purporting to show that the central claims of Judeo-Christian theology are in fact true. I've been forced into these conclusions by the inexorable logic of my own special branch of physics." Now, I think he might be reading too much theology into physics, but I think the fact is that he saw this as evidence for God, and it had a really big impact on his life. And he wasn't really looking for it or expecting it. And so I think that's worth noting. Here's some recommended resources, some good authors. In particular, at this point, I would say the best book out there is definitely this new one, seen just to the right of the letters there, A Fortunate Universe by Lewis and Barnes, available now in Kindle form, or if you're in the UK, I think you might be able to get it in hardback form as well. All right, and that concludes the presentation. Sorry if that was a little long, but we can deal with questions now.
Thank you, Alan. That was fascinating. If any of you would like to ask questions of Alan or make comments or express disagreement or anything else, then you can raise your hand and I will promote you to be a co-panelist with Alan and ask your questions. We have 2 hands raised at the moment. Let me just, I have just a couple questions that I thought I would ask. First, Alan, so the 3 categories of explanation are typically offered to explain the cosmic fine-tuning, or chance, necessity, and design.
Yes.
The necessity hypothesis, which is to say that our universe is finally tuned out of physical necessity, the constants and laws just had to be the way that they are. That seems to me to also itself require, it's still a probabilistic coincidence, because it's a probabilistic coincidence that what is necessary, what exists out of physical necessity, just so happens to coincide with what's necessary.
That's right. The argument would still work at the level of logical possibilities, even if it didn't at physical possibilities.
So then the necessity option's off the table. So then we're just left with the chance hypothesis versus the design hypothesis. And then the chance hypothesis obviously runs into all the problems with the multiverse hypothesis, which is the only real viable incarnation or manifestation of that hypothesis. And so since the chance hypothesis clearly fails or is so implausible, that leaves the design hypothesis as the best candidate explanation.
Yeah, nice summary of a way to make the argument without the Bayesian aspect. Yeah, that's kind of how William Lane Craig posits the argument. And it's I think it's a reasonable approach, and I think Luke Barnes has said he thinks that's a reasonable approach as well.
Another point I was thinking, often when I make the fine-tuning argument and someone brings up an objection to probabilistic coincidence arguments, and say, well, it's we only have one universe, or it already happens, the probability is 1, or they say that it's no more improbable than any other given sets of laws and constants. I often use that as, I often point out that this is making those sorts of objections to probabilistic coincidence arguments is really a double-edged sword, because it cuts all the arguments for common ancestry, because all the arguments for common ancestry are based on probabilistic coincidences.
That's right. I mean, it's very common in science to make those kind of arguments. So if that fails, then science has big issues.
Okay, let's bring up someone else. Let's bring up James. James, you're on.
Hello, James.
Hello. Hey, Alan. This isn't totally related, but have you ever seen Babylon 5? Are you familiar with who the Minbari are?
I have not.
Okay, I won't use that analogy then.
Sorry.
That's okay. That's okay. There may be, I don't know how vigorously this has been pursued or if you've encountered it or not, but with the idea of fine tuning versus total chaos, have you ever encountered something along the middle, something more along the lines of something that Yoda or a Jedi might say? The idea of the I don't know if I'm pronouncing it right, but the elan vital, that the universe has this built-in X factor that naturally tends toward organization, and that tendency toward organization has led toward life. And it seems surprising, but because this X factor that lends itself naturally toward organization is there, it's no more surprising than that once you have gravity, the planets are spheres instead of cubes, and water flows downhill. Do you have any comments about the proposal that the universe just happens to have this built-in self-organizing aspect to it? Not really a consciousness, but just.
Well, are you saying that it just happens to have it, or are you saying that somehow there's some? I mean, are you implying that there might be some, whether personal or impersonal, some force that drove it in a certain direction, or are you saying that they just happened to be this way, kind of thing?
As far as we can tell, there's no force behind it. This would be the force that drives self-organization. That it's just a natural built-in force, like gravity would be a natural built-in force. And I think the term is again the elan vital. Have you ever encountered any of Bergson's old writings?
Not very up on that. Sorry. But yeah, I've certainly heard, similar kinds of things proposed, that maybe there's something of that nature. I think I would find that very surprising, at least on atheism or naturalism, even if you're going to attribute this kind of fine tuning to something of that nature. It's like, well, why would it be that way if at its most fundamental level, the physics, the constants, there is nothing to drive the constants to life permitting values on naturalism or atheism. And yeah, we don't get a lot of specificity on, the nature of a designer, but I think that would almost sound like a type of design. If there's something that can act on the universe and drive it in a certain direction, I mean, there's teleology inherent in that. And I think naturalists and atheists are generally anti-teleology in nature. So those are my thoughts anyway. Do you have anything to add, or?
Just if you, I'll give it back to Jonathan. I think that does it for now.
Okay.
Okay. We also we have Kevin Ross, who is a physicist, so this will be interesting. Kevin, you're on.
Hello, Kevin.
Hello, Jonathan. Hello, Alan.
I'm good. Long time no see, Kevin. Haven't seen you since 2010.
That's right. That's right.
Wow.
Hey, I just want to make a comment. I loved your presentation. I think there's a lot of compelling evidence to support cosmic fine-tuning. But you were deliberate in kind of shunning away or shying away from the environmental fine-tuning. When you think about the fact that cosmic fine-tuning and environmental fine-tuning are both necessary conditions for the possibility of complex life. Therefore, you kind of think that the probabilities of naturalistically coming up with something like life is going to be a product of the probabilities, which are both infinitesimal. And then you say that, okay, now these are both necessary conditions for even starting to talk about the possibility of producing the biological information required for life. So,
yeah, it might be a good part of a cumulative case argument. I mean, personally, I'm still kind of in the evaluation phase on that argument. I do think it's harder to assess the probability. We know there's a lot of planets out there, and I do think there's good reasons for thinking that Earth-like planets are incredibly rare, but I don't feel confident enough to say how rare, or there's also the possibility, even with a version of inflation that wouldn't lead to multiverses, you might well have a vastly larger universe than what we have, and therefore there might be more chances than what we're aware of. And then there is an anthropic selection effect coming into play then that would allow us only to observe the life-permitting ones. I think it is a decent part of a cumulative case, but I do like sort of not mixing that with this argument, because you're on firmer ground, in my opinion anyway, with the physics of the constants, initial conditions, and laws. There seems to be a little more uncertainty in the environmental aspects. But at the same time, I think those are interesting. I'm trying to learn more about them. I'm trying to be conservative in evaluating them. And there may be some, I just kind of view it personally as like there's some evidence there, but it's just, to me, it seems so much weaker than this other evidence that I feel more compelled to really focus on the core cosmic fine-tuning than the environmental parameters. But part of that might be, I'll admit, my own, haven't studied it in enough detail. I think there's so many different things to really think about and consider in that you've got to be careful. But I do know a friend of mine, Mike Strauss, OU physics prof, he finds that very compelling, and he's pretty knowledgeable. I've read The Privileged Planet and thought through some of that. I think there's also something to be said for the fine-tuning for discoverability, where Einstein said the most incomprehensible thing about the universe is that it's comprehensible. And Eugene Wigner in his writings about the amazing aspects that we can model the physical world in mathematics, I think there's some force in that might come into play here also, and arguing for theism over the multiverse. But yeah, I probably need to study a little bit more about those, but I think even in principle, it's going to be harder to make that case than it would be for this other case. But I'm glad you brought that up, and that those are things that are important to evaluate. Exactly how improbable, do you have a rough feel for how improbable you think it would be to have a life-permitting Earth, a planet that could permit life?
Well, I know that this is an active area of research in NASA, and I think that it's a popular area. The whole idea of finding Earth 2.0 has a lot of a popular appeal, and this is one of the reasons why I suggest that it may be a strong way to argue, because people may not be able to understand the vast improbabilities implied by cosmic fine-tuning. However,
that is true.
They may be able to understand that perhaps there's only one habitable universe like Earth in the entire visible universe.
Well, yeah, the other thing about this argument in general is that it seems that many scientists, many of those NASA types, seem to think that yeah, there could be lots of life permitting planets out there. Whereas in this physics area, the arguments I'm making, you're appealing to things which it seems like the experts in that field really agree with in detail. So that's another reason maybe in favor of the cosmic fine-tuning argument, is that you really are arguing from mainstream physics to a philosophical argument for God. Whereas in the other case, you might at least have some uphill battles against some scientists, from what I understand.
Yeah, perhaps. I'm just thinking about the Privileged Planet video. It seems that some of the main players in the public research really seem to be thinking along the same lines that we are.
Yeah, there's certainly some, there's some that recognize that it's far harder than most people think to have a life-permitting planet and so forth. The other thing about the Privileged Planet is their main thesis was more to do with wherever you find a life-permitting planet, it's going to be discoverable. And even they weren't, in some sense, arguing that there wouldn't necessarily not be a lot of life-permitting planets, but just that if there were, they would be in areas where you could also, or well-suited for scientific discovery. And part of that may be that once you're open to theism, that may make it more likely that there would be other life-permitting planets in other parts of the universe. To me, anyway.
Right. I honestly like the idea of the privileged planet hypothesis, but I don't find it necessarily compelling. It's just an interesting idea.
Yeah, I think they wanted to have something which was very falsifiable and that they did have some pretty strong evidence for, but yeah, I don't think they were saying it was the final word or anything like that, but it'll be interesting to see how this plays out as we learn more about other planets and suns and so forth.
Very good. Thank you very much for your presentation.
Thank you, Kevin. Nice to talk to you.
Alan, by the way, have you read Michael Denton's work where he talks about some other finely tuned things, such as his new book, for example, Firemaker, where he argues that our planet seems to be finally set up for discovering and utilization, manipulation of fire?
Yes, I have, and I think there is some force to that, and Robin Collins has done some good work as well on the fine-tuning for discoverability that I think those are more quantifiable too, by the way, than necessarily knowing the probability of a life-permitting planet across our vast universe. I think that's challenging to really bound that in a way that you can make a real compelling argument. So I think it's probably more promising that those kind of arguments where you can show that, hey, if the fine structure constant was just a little bit different, we wouldn't have been able to forge metals and have fire and all that. So yeah, I think those are worth considering as well. And you fold them into a cumulative case argument, it just makes this all the more probable.
Yep, I'll need to ask Denton to come on and talk to us about that, because that would be right.
That would be great, yeah.
Let's bring up Robert Wells again. Robert, you're live. Go ahead.
Can you hear me?
Yep.
Okay. So if I'm understanding this multiverse thing, I've actually watched a few TED Talks with various physicists, and they talk about the multiverse thing. And it's kind of interesting. They bring up the thing that there's three things that could explain the creation of the universe. And the first one always is God, and they all laugh at that. You can go watch the TED Talks, and they're like, oh, yeah, people believe in that God thing. But no. And then go to the multiverse, and they all seem to accept this and embrace this as somehow rational and possible. But the thing is,
they seem to be on the same metaphysical par, so to speak, in terms of the ability to directly get observational evidence for them. But.
Right. Well, the thing is, and I watch these, and I'm thinking, well, how does this explain away God? I mean, it seems to me if you get the multiverse, especially after watching your talk, that all you've done is basically polluted the probability pool. It's like adding decks to a blackjack run. You can add as many decks as you want, but if somebody still keeps winning, they're going to get banned from the blackjack table. They're going to be thrown out of the casino because obviously they're doing something, kind of wrong, like counting cards. But yeah. The interesting thing, though, the question I have, I guess, in this multiverse thing, can we interact with these multiverses? can we get information from or send information to? And if the answer is no, then it's kind of irrelevant, because the only universe that matters then is ours. And even if there are multiple universes, still doesn't explain away God, because something had to create these multiple universes. You know what I mean? To make it just right for us. So
yeah, you bring up some good points, interesting things to discuss. I think we do have to be careful to make sure we're accounting for the anthropic principle as far as multiverses. If we knew for sure that there was an oodle just vast numbers of other universes, and they had varying laws and constants and so forth, then after you have to apply a selection effect. Well, any observers in any of those universes are only going to be in ones that permit observers. If the multiverse, I think, passes all those tests that I gave, then I think it could be an adequate explanation. But I think you bring up some good points as far as it's certainly not anywhere close to passing those now. There seems to be, and by the way, there would be a variance as to whether a multiverse is detectable or not. Depends on the theory. But it is the case that in many of these theories that it is even in principle not detectable. And therefore, it would be at a different kind of epistemic level even than the proposal that God exists. Because for a theist that's not a deist, you do believe that God is involved in the world, he's acting in the world. There may be detectable means you can evaluate concerning God. But if these other universes had no interaction whatsoever with our universe, then even in theory, wouldn't be able to ever get any actual evidence for them in a direct way. And this ties into the quote I read by Susskind, where he says that there's a dilution of the scientific method involved in believing in these multiverses because of this issue. So that's something to think about. There have been some like George Ellis that are really pushing back on multiverse theory, saying that you guys are moving away from science. And he'll be the first to say it's fine as a metaphysical idea to consider, but he wants to be careful in how scientists make proposals about multiverses. But I think there are some ways, the kind of things that we were trying to establish in that presentation, we want to look at, well, what does a multiverse theory predict? If it makes predictions that we can detect in this universe, and enough of them turned out to be true, then it might be reasonable to accept it as an explanation. But so far, it certainly doesn't seem to be the case that is the case. Where it's not predicting universes like ours or observers like ours. So I think there's some severe problems with the multiverse, at least as an explanation of fine-tuning. That's nothing to say. I have no real opinion about whether there are other universes. I don't know. I don't think we have much evidence one way or the other on that. It's certainly possible for theism or naturalism that you could or couldn't have them. We just have to follow the evidence where it leads on that. But as an explanation of fine-tuning, I think there's several problems with at least any of the current multiverse theories that I'm aware of.
Just quickly, just to follow up on that of interest, do you think, Alan, that there's any reason to think that even if there is a multiverse, that is there any reason to think that all of what you might call constant space is occupied? Because what reason do we have to think that even given an infinite array of parallel universes, that it's occupying all of constant space?
In other words, the parameter space you're talking about?
Yeah.
Okay. Yeah. That's a good point. I mean, I think within different theories like string theory, they're looking at these vacua, they call them. They're looking at how can you collapse the 11 dimensions? How can you compactify them into three-dimensional space? Depends on the number of ways of doing that and how the string theory works at a fundamental level. And I don't know that much about string theory, I'll be the first to admit, but in studying about how they talk about it in this context, it sounds like there are finite numbers of them based on how there's this Calabi-Yau manifold that relates to this compactification. So it depends on how many low energy states or vacua are there once you do this compactification. And some ways of doing it might lead to very large numbers of them. As I mentioned, this 10 to the 500th that's off quoted. And so that would probably be plenty for explaining the fine tuning. But, you know, how do we know that string theory is true? And even if it is, you still also need a universe generating mechanism. And then you need to look at the predictions of that multiverse. And so far, that they don't seem to be, you know, very good if our universe is this different.
And it seems that if you have a universe generating mechanism, then it's very difficult to see how you could avoid that being finely tuned as well.
It is, I think. Yeah, I mean, that doesn't seem like the easiest kind of, if you were thinking of making a machine like that, it doesn't seem like the easiest kind of machine to make that would just crank out huge numbers of universes and so forth.
Especially with all the different combinations of constants and everything.
And one of the problems you have is that I think people are led towards these theories that produce huge numbers, because then the fine tuning is not a problem. But it's almost like that's where you get into the Boltzmann brain type problems. If there's too many of these other universes, it tends to be really hard to end up predicting large, finely tuned universes as opposed to Boltzmann brains or smaller universes that don't require as much fine tuning.
Mm-hmm. Let's bring up James here. James, go ahead.
So following up on what I had asked earlier, is there anything you're saying today that about a theistic universe that can't also apply to a pantheistic universe?
Let me think about that. So on pantheism, the universe is basically God. Everything is sort of God. And so there could be within that such a universe some mechanism that would favor then order, complexity, life, etc. I mean, I think the fact that we have good reasons from physics for thinking that the multiverse is not eternal, or the universe isn't in its broadest conception, argues against pantheism. But I don't know, yeah, maybe not from the fine tuning itself. Maybe you don't get anything to distinguish, but I'd have to think about that more.
I think I would say to that if you suppose a pantheistic universe where the universe is God, and you have God that is basically defined by physical laws and constants, that's a very complex God, and God by definition is a necessary being. Are we really saying that? I mean, God in a classical sense, in a sort of Judeo-Christian classical sense, is not comprised of parts. He doesn't have laws and values and physical constants, and so he's very simple as an explanation. So God is simple. He's a necessary being, exists out of logical necessity. And so I think that a theistic universe should be preferred for that reason over a pantheistic universe. Not to mention, as you said, that our universe clearly began to exist. We have good philosophical and scientific reason to think that's the case.
Yeah. My question though isn't which is the superior view. It's just that when we see evidence for fine tuning, couldn't that all be applied just as well to a pantheistic universe as to a theistic universe? Or to put it another way, to an impersonal God rather than a personal God.
Perhaps. Well, go ahead, Jonathan.
I was going to say very quickly. I think that that if God, if you would need a basically it would lend credence to the old schoolboy question of who designed the designer, because the God that is the universe would itself require another independent designer who designed it because of all the finely tuned constants and parameters. Unless you're saying it's a self-designed designer, which it really is philosophically, logically problematic. So you would need something.
Yeah. Well, I think it would throw the initial cause back, I think, to the how did the hydrological cycle begin? There had to have been something else before that, but could we people could just say that's what we're looking at to the realm of mystery, and just say here's what we can find out about it. Can't that apply just as well to a pantheistic a God rather than a personal God. And so that's what I was asking about. So, but I think you got the answer. So back to you.
I've always thought that pantheism has a much more significant problem with the problem of evil than would theism, because then the universe itself is God, and how do you explain some of the evil in the universe on that basis?
Well, yeah,
that's probably off topic a lot.
Yeah, I'm glad I don't have to try to defend that one. I'm not a pantheist, but just
Sure.
looking for ways to address the question and fill it
No,
back.
it's a good question, and it got me thinking, as I haven't really evaluated it from that standpoint much. I guess because I have a bias against pantheism, but
Also, Alan, pantheism undermines dualisms. And so then the moral argument becomes far more severe if you deny dualisms as well, which is also...
Well, yeah, because the whole concept of evil, the solution isn't so much conquering evil as ceasing to care about it, detachment.
So, sorry, say that again, James?
In pantheism, the idea of the basic idea of what do you do about evil, the solution to evil isn't so much to conquer evil as it is to stop caring about evil, to be detached, to have detachment about it.
Right.
yeah, at least in some of the Eastern religious expressions of pantheism anyway, yeah.
Yeah. But I don't think it solves the fine-tuning problem, because then you would need a designer to design the designer, and it would be very difficult to conceive of such a pantheistic God being a necessary being.
Yeah. Well,
Every
I
world.
don't want to speak for the pantheists, but they would probably say at a certain level there is no design; it just is that way.
Which is to invoke the necessity category of explanation, but is you still require some explanation for why our universe, whether it's a pantheistic universe or otherwise, is finely tuned. You have some explanation for that.
Well, in the words of that great pantheistic philosopher Yoda, there is no why.
Yeah.
Just to let you know, Jonathan, I have about 30 more minutes, and then I need to get going.
Sure, of course.
So I can go speak on this again.
All right. Well, thanks, James. We have some submitted questions. Let's just run to get some of those, and then we can begin to wrap up. If anyone else has any final questions that they want to raise their hand about, then now is your opportunity to do so. In the meantime, I will read what we have submitted. See, I'm just going to read Rod's questions you've already addressed. He says, the fine-tuning argument appeals to divine psychology that a God would create intelligent life. We have no idea how likely this is. And yeah, you've already addressed this. No matter how improbable it is that God would create life, it's still going to be more probable than that we get intelligent life on atheism. So
unless you can be so, more sure than, say, 1 part in 10 to the 50th power that God wouldn't want life, then you're not going to defeat the fine-tuning as some evidence for God, at least.
And I think the only way to really argue against the Bayesian formulation of the fine-tuning argument is to argue that the anterior or prior probability of God is so astronomically small that that counterbalances that evidence. But I think really the burden of proof has to be shouldered by the atheist who claims it's that low.
Yeah, and I like the way Robin Collins coins it, just dealing with more of, independent of what your prior is, we want to make the point that this should make it more likely that God exists than it was previously. You can do some Bayesian updating and so forth, but it wouldn't undermine it as evidence for God, even if it didn't end up making it more likely that God exists for a given person if they had this really low prior.
But I think so.
But yeah, it would take a really low prior, wouldn't it, to overcome this? It would seem.
But would you agree with me that the atheist has to shoulder the burden of proof on that one?
I would, yeah, to justify a prior of 10 to the negative 40th or something like that. I don't know how you would justify that, but.
Let's see. Chris Kloss says, given the multiverse theory, can this theory be explained in an eternal sense, or would the multiverse have to have a beginning point?
Well, I don't know how much you've talked about this in previous times. That's more to do with the origin of the universe than the fine tuning. But I do find some power in the Bourdais-Vilenkin-Guth theorem that seems to argue that on very general grounds, even a multiverse would have had to have a beginning. And it seems like the main assumption made there is that the universe has on average expanded, and it's very difficult to overcome that without flying in the face of the second law. And I think Aaron Wall has done some good work on a generalized second law in showing that there doesn't seem to be an out from quantum mechanics to a second law type principle. But certainly a lot of cosmologists are striving hard to find a way to make the universe eternal. They're proposing models, but there's a long history of failed attempts. And I find it interesting that even someone like Lawrence Krauss would say, well, I think he would try to really diminish, he says, you can't say, that the universe had a beginning or something, but even he would say it seems more likely that it did. And that raises some severe problems for it, as in many ways, I think.
And we also have philosophical reason to think that the universe must have a beginning, because you cannot traverse an infinite amount of time.
Yeah, and even if that argument doesn't work, I think some by like Alex Proust, that in applying it specifically to time seem to have some force. So yeah, I think there's definitely many good reasons for thinking that the universe is finite to the past, even if there was something before the Big Bang.
972 wanted to ask, wouldn't a multiverse create the problem of an infinite regress?
Well, I think you certainly have a problem for atheism or naturalism if there was an origin of the multiverse, because it seems rather inexplicable. It seems to point to a transcendent cause, etc. Now, as far as with respect to fine-tuning, I mean, independent of whether you have the possibility of an infinitely old universe or not, let's just say in the context of fine-tuning, you have some multiverse theory that if you've shown it plausible, then there's probably a way that it could be an adequate explanation by avoiding the infinite regress problem. But the infinite regress type thinking is what leads them to some of these things that are considered to be proofs against an eternal universe. So I think he's on to something about the infinite regress, but it has a lot more to do with the origin of the universe than fine-tuning.
Jason McCool asks, from my understanding, Dembski estimates the maximum probabilistic resources of the observed universe as a way to say anything with worse odds can be taken as impossible. But I got some pushback recently that the multiverse skirts that issue by multiplying probabilistic resources, but it seems like that would only be the case if the individual universes were somehow connected to pool resources. Otherwise, isn't each universe an isolated resource pool?
Yeah, that's a great question. Yeah, I understand Dembski came up with this one, I guess 10 to the 150 or something like that as a sort of a maximum bound. And that was based on our understanding of the size of our universe. And our universe may be bigger than the visible part. It's very reasonable to think it might be significantly larger than that. But I think, the thing that gets interesting here is that you also are trying to account for an anthropic selection effect. Observers can only observe themselves in a life-permitting universe. And so it makes it a little bit more complicated. There's been interesting work done by some philosophers on this topic. And there's a physicist named Halonen that does a Bayesian analysis where he points out that if these are disconnected, if they don't make it any more likely to have life in our universe, that a normal Bayesian way of working through the probabilities would show that it's irrelevant. And then Roger White, as a philosopher, who's argued that you have to have independent evidence. I think this is certainly true, that you would need some independent evidence for a multiverse before it would count as an explanation for life in our universe. Mm-hmm. And I do think that's fairly lacking now. There's some theoretical reasons for thinking there might be a multiverse, but I would put a pretty low number on that if I was doing some overall probabilistic assessment, reasonably low anyway.
And it's not just any multiverse that's required, but certain particular types of multiverses which can explain the fine-tuning of our universe.
Exactly. That's a key point. So often people will just throw this out like, well, if we've got multiple chances, then we don't have to worry about it. But you got to have, there's some additional baggage there, and that's where Occam's razor can come into play. I agree with physicists that would say the concept of the multiverse itself should not be argued against on the basis of Occam's razor, because it might be just a simple outworking of some fundamental laws. But as an explanation for fine-tuning, as I tried to show at least, there seems to be that you have to conjoin numerous hypotheses together before it's an adequate explanation. And that does come into play, at least in some minor way, with Occam's razor, which is just a heuristic anyway. But it points to you've got to overcome several hurdles before it's an adequate explanation.
And also, you have to your exploration of parameter space, if you will, must stick to the constants and values associated with our universe. I mean, imagine that you had a completely different type of universe with completely different sets of laws and constants, like there was completely different physics. Well,
yeah.
What reason is there to think that it's the same physics in each universe? And so that really amplifies the problem, I think.
Well, that's complicated, I think. I think the assessments for fine-tuning thus far are based more on, we're assuming the same physics and we're varying the constants.
Exactly.
And that's something that we can assess fairly accurately, probabilistically. But if you just say, well, the laws could have been anything, anywhere, I think it becomes very hard to quantify it, at least at that point.
I agree.
He's done some good, he's pointed out some things related to Conway's game of life and how they worked so hard to come up with a set of rules that would lead to complexity. And on general grounds, you could think that it would seem to be hard just to come up with laws that could necessarily be life permitting. And indeed, if you start thinking about the laws of our universe, if you start changing things, if you get rid of any of the four fundamental forces, you wouldn't have life. Maybe the weak force is a little debatable, but they only overcome that by fine-tuning. If you get rid of quantum mechanics, atoms are not stable. If you get rid of the Pauli exclusion principle, you don't have the kind of chemistry you need. So there's about 20 things like that I think Robin Collins has pointed out that if you were to randomly change laws, there's a bit of an argument there too. It's harder to quantify though. But I think that, we can make good arguments within our epistemic limits. And it is more, the physics has made incredible progress by assuming the laws apply to the far reaches of the universe. Do we really have a good basis for saying, hey, even at the level of laws, they're totally different. There's no quantum mechanics if you go out enough light years or something like that. Does that really make sense? I don't know.
But the multiverse objection to the fine-tuning argument presupposes that each of these universes in this universe ensemble, or this multiverse, if you will, has the same physics. Because if they all have completely different physics, then it doesn't really explain the fine-tuning of this universe with respect to our physics.
That's right. There is a guy, Tom Banks, a physicist, that he thinks maybe string theory would entail differing laws. And I think it just becomes somewhat inscrutable at that point to do anything in a rigorous way anyway, to know exactly how improbable it is. But again, string theory it's got a long way to go before we can really draw many conclusions or analyze it in any detail when you can't even write down the equations for it at this point.
Right. And as to Jason's question, from what I would say in defense of Dembski is when he wrote his books, The Design Inference and No Free Lunch, he was speaking specifically about biological complexity rather than the physical fine-tuning. And so there is a different form of argument that he was making there. And if you're explaining life in this universe, then you can put those, his probabilistic analysis does apply to, from what we know, how many chances do you get, how many different chemical reactions, etc. So that's a reasonable thing to consider. But, there is Eugene Koonin, who I think is a skeptic. He's argued you need something like the multiverse just to explain life, which I find rather interesting. But yeah, I've seen that. Okay, we don't have any submitted questions. Do you have any last minute burning questions that anyone wants to ask before we wrap up? I'm surprised there's no atheist tonight. We're giving Alan a free ride.
I really wanted some skeptics. Come on, guys.
Maybe they'll be being silenced by the strength of your argument tonight, Alan. All right. Well, I don't think there's any more, so let's wrap up. Thanks so much, Alan, for being with us this evening. It's been great.
Thanks for the opportunity, Jonathan, and thanks to everybody for the great interaction, and I really appreciate it.
Great, and just to remind folks, here next week we have George Yancey talking to us about Christianophobia. We've all heard of Islamophobia and homophobia, but have we heard of Christianophobia? Well, George Yancey is going to be talking to us about that. He's a sociologist in Texas. If you want to visit our website, it's apologetics-academy.org. And if you click on online apologetics training, you can find the schedule for upcoming sessions as well as peruse recordings of past webinars as well. And I'll be putting this recording for this webinar up on YouTube and probably on Monday. So again, thanks all for coming. So thanks, Alan.
Thanks a lot. Take care.
See ya.